Imagine a scenario where a renowned composer travels backward through time and gives an ancient symphony to Mozart before Mozart was even born, and Mozart then develops this very same composition, eventually publishing it under his own name, which is how the composer discovered it in the first place, creating a closed causal loop where the music exists but was never actually created by anyone, emerging from nowhere into reality fully formed and perfect. This is the essence of the Bootstrap Paradox, perhaps one of the most intellectually unsettling paradoxes in the entire landscape of time travel philosophy and temporal mechanics. The paradox takes its name from the phrase, pulling yourself up by your bootstraps, which is physically impossible, much like the paradox itself seems logically impossible, yet it presents a genuine problem for anyone who accepts the possibility of backward time travel while simultaneously believing in the conservation of information and the principle that something cannot come from nothing. Consider the mechanics of this scenario more deeply and carefully, for it reveals something profoundly strange about the nature of causality, creation, and existence itself. In the traditional formulation, a person travels into the past and delivers a specific piece of information, an object, or a creative work to someone who then becomes responsible for creating or distributing that very thing in the original timeline, thus forming a circle of causation that has no beginning point and no originating source. Yet somehow the information or object persists as though it had been created legitimately. The information seems to exist in a state of ontological suspension, real enough to be transmitted and used, yet never actually originating from any creative act or external source, simply cycling through time eternally without any explanation for how it entered the universe in the first place. The psychological mechanism that makes this paradox so disturbing operates on several levels simultaneously, striking at the heart of our fundamental assumptions about creation, originality, and the flow of causality through time. We are deeply accustomed to the idea that all information, all objects, all creative works must originate somewhere in time, that there must be some first cause, some original creator, some moment when a thing began to exist before it could be transmitted forward to other times and places. The Bootstrap Paradox violates this assumption by suggesting that information could exist eternally, circulating through time in a closed loop, never actually being created or invented by anyone, yet remaining perfectly coherent and functional. This strikes at our understanding of how knowledge works, how creation functions, and how the universe maintains logical consistency, and this is why contemplating it for extended periods can produce a distinctly unsettling sensation in our minds. From a purely logical standpoint, information should require a source, and that source should be located at some point in time before the information is transmitted elsewhere. Yet the Bootstrap Paradox describes a situation where this linear progression of causality breaks down entirely, where the information seems to exist in defiance of temporal order and logical necessity. The mechanism that allows us to even consider such a thing as possible is our acceptance of time travel as a genuine physical possibility, a notion that has gained surprising credibility among theoretical physicists who have discovered that Einstein's equations of general relativity do not explicitly forbid closed time-like curves or backward time travel under certain exotic conditions. Though the practical engineering of such phenomena remains firmly in the realm of speculation and theoretical possibility, rather than achievable technology or observed phenomena. We have normalized this paradox in our collective consciousness by incorporating it into our popular fiction, our science fiction narratives, and our philosophical thought experiments, yet despite this normalization, we have not actually resolved it, nor have we developed any universally accepted mechanism for how it could actually function in reality. Some physicists and philosophers propose that the Novikov self-consistency principle might provide a solution, suggesting that the universe would simply prevent any action that would create a paradox, meaning that any attempt to travel back in time and alter events would fail in some subtle way, or that the timeline itself would branch into an alternate reality, thus avoiding the logical contradiction altogether, though this raises its own questions about the nature of free will and causality. Imagine yourself standing at the precipice of temporal mechanics, contemplating a scenario so deceptively simple yet impossibly complex that it has troubled physicists, philosophers, and science fiction enthusiasts for generations. You possess a time machine, a marvel of engineering that defies the conventional understanding of causality and linear progression. You travel backward through the corridors of time to a moment decades before you were born, to the era when your grandfather was a young man, perhaps not yet married, perhaps walking through a city street on an ordinary afternoon with no knowledge that his life was about to intersect with something extraordinary. In this imagined scenario, you make a choice that seems logical from your perspective, a choice born from curiosity or perhaps darker motivations, and you decide to prevent your grandfather from ever meeting your grandmother. You might accomplish this through countless methods, each theoretically viable within the framework of your time travel capabilities. Perhaps you separate them before they ever meet, or you ensure that circumstances prevent their relationship from ever developing into something meaningful. Or in darker interpretations of this paradox, you eliminate your grandfather entirely, removing him from existence before he could father the child who would eventually become your parent. And here is where the logical machinery grinds to an impossible halt. If you succeed in your mission and your grandfather never meets your grandmother, then your parent would never be born. If your parent was never born, then you could never have been born into existence. Yet if you were never born, then how is it possible that you traveled backward through time to accomplish this act in the first place? You would be erasing the very chain of causality that created you, uncreating yourself retroactively, existing in a state of logical contradiction that seems to violate everything we understand about existence and causation. This grandfather paradox, as it has come to be known, represents one of the most fundamental challenges to the concept of time travel as we typically imagine it. The paradox operates on a beautifully simple logical foundation that requires no advanced physics or complex mathematics to understand. It demonstrates that if time travel to the past were possible in any conventional sense, it would create logical contradictions that appear to be unresolvable within our standard frameworks of cause and effect. The mechanism behind this paradox is rooted in what philosophers call the principle of non-contradiction, the idea that something cannot simultaneously be and not be in the same respect and at the same time. You either exist or you do not exist. Your grandfather either was killed before your birth or he was not. These states cannot coexist, and yet the grandfather paradox seems to demand exactly that impossible coexistence. The psychological appeal of this paradox lies in its accessibility and its immediate intuitive power. Unlike many theoretical physics problems that require extensive mathematical training to grasp, anyone can understand the basic setup of the grandfather paradox within seconds. A person travels back in time and prevents their own birth. This creates a logical knot that cannot be untangled through conventional reasoning. We find ourselves drawn to such paradoxes because they illuminate the hidden assumptions we make about how reality operates. We assume that the past is fixed and unchangeable, that history has already happened and cannot be altered. We assume that causality flows in one direction only, from past to future, and that our actions in the present are determined by what came before. The grandfather paradox challenges these fundamental assumptions and forces us to reconsider the nature of time itself, whether time is truly linear or whether it possesses properties we have not yet discovered or understood. What makes this paradox particularly fascinating is that despite its logical impossibility, we continue to explore it, discuss it, and attempt to imagine solutions to it, much as one might wrestle with an unsolvable koan in meditation. We have developed various theoretical frameworks that attempt to preserve the possibility of time travel while avoiding the logical catastrophe of the grandfather paradox. Some physicists propose the many worlds interpretation, suggesting that traveling to the past would create a branching timeline where you prevent your grandfather's meeting in an alternate universe, leaving your original timeline unchanged. Others suggest that the Novikov self-consistency principle applies, meaning that any attempt to create a paradox would be prevented by chance events or circumstances beyond your control, ensuring that the timeline remains logically consistent. Imagine you possess a wooden ship, a vessel that has carried you across countless voyages, weathered storms, and witnessed the passage of years in service. Over the course of time, the wood begins to deteriorate as all material things do, and you find yourself replacing one plank after another, then the masts, then the sails and rigging, until eventually every single component of the original ship has been swapped out for new material. The question that emerges from this seemingly mundane process of maintenance is deceptively profound. Is this still the same ship you originally owned, or have you gradually constructed an entirely different vessel without ever realizing the transition occurred? This ancient paradox, attributed to the philosopher Hobbes and traced back through Plutarch to the original Ship of Theseus in Greek mythology, strikes at something fundamental about how we understand identity, continuity, and what it means for an object to remain itself through time and transformation. The paradox deepens when we introduce a complication to this scenario. Imagine that a meticulous observer has collected all the original planks as they were removed from the ship throughout the years, preserving them with care, and then assembles them back together into a ship configuration using the original construction methods and materials. Now you have two ships, one that has existed in continuous operation with complete replacement of parts, and another made from all the original material reconstructed according to the original design. Which one is the true Ship of Theseus? The one with historical continuity and continuous function, or the one composed of the original physical matter? Most people find themselves drawn to both answers simultaneously, unable to definitively choose without discovering contradictions in their reasoning. The psychological mechanism underlying this paradox reveals something essential about how human consciousness assigns identity and ownership to objects. Our brains rely on several competing criteria for establishing what makes something the same thing over time. We consider physical continuity and material composition. We consider spatiotemporal continuity and unbroken existence. We consider functional continuity and purpose. And we consider the narrative continuity of how something got to where it is. When these criteria align, we have no problem saying something is the same. But when they diverge and point in different directions, we find ourselves without an objective answer, only preferences. We intuitively feel that gradual replacement should preserve identity, yet we also feel that original material composition should matter deeply, and when forced to choose, we cannot articulate a principle that isn't undermined by some aspect of the scenario. What makes this paradox particularly compelling is that it is not merely an abstract puzzle confined to philosophy classrooms. This exact problem manifests throughout human experience in ways we have largely stopped questioning. Every cell in your body is replaced approximately every 7 to 10 years, meaning the physical material composing you now is almost entirely different from the material that composed you a decade ago, yet you remain yourself with continuity of memory and identity. Your automobile receives replacements of batteries, belts, filters, and major components throughout its life, yet you continue to refer to it as your car without hesitation. Civilizations rise and fall, people emigrate and settle, governments reform their structures, institutions transform their purposes, yet we grant them the same names and treat them as the same entities across centuries of change. We have normalized the paradox so completely that we rarely notice its constant presence in our daily existence. Perhaps most strikingly, we encounter versions of this paradox in social and institutional contexts where the stakes feel considerably higher than a hypothetical wooden ship. A nation's population might turn over entirely across generations, its government structure might be revolutionized, its borders might shift, its founding principles might be reinterpreted or abandoned, and yet we insist it remains the same nation with rights and responsibilities stretching back through history. A company might replace every employee, relocate entirely, change its core business, alter its ownership structure fundamentally, and still claim to be the same company with the same legal identity. These real-world applications reveal that the paradox is not merely interesting as a logical problem, but rather points to something about how human consciousness creates continuity and identity in a constantly changing universe. The persistence of this paradox, despite its apparent unsolvability, suggests that there may be no objective fact of the matter regarding identity through change and replacement. If you consider the sheer vastness of the observable universe, a number so incomprehensibly large that our minds struggle to grasp it, you are confronted with a question that has haunted scientists, philosophers, and dreamers for decades. Where is everybody? This is the essence of the Fermi Paradox, named after physicist Enrico Fermi, who posed this question during a lunch conversation in 1950, fundamentally challenging our assumptions about life in the cosmos. The universe contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars, and current astronomical evidence suggests that planets are extraordinarily common, orbiting around most stars in existence. Given these astronomical numbers and the fact that life emerged on Earth through processes governed by chemistry and physics that presumably operate everywhere in the universe, it seems statistically improbable, almost absurdly unlikely, that Earth is the only world harboring intelligent life. Yet despite centuries of observation and decades of dedicated searches using sophisticated radio telescopes and other detection methods, we have found absolutely no confirmed evidence of extraterrestrial civilizations, no radio signals, no visiting spacecraft, no artifacts, no signs whatsoever. This is the paradox. The universe should be teeming with life, yet it appears to be eerily, profoundly silent. The psychological and logical mechanism underlying this paradox operates on a foundation of probability and time scales. When Fermi performed his famous calculation, he reasoned that even if intelligent life is extraordinarily rare, requiring billions of years to develop and persisting for thousands of years, the universe is so incomprehensibly old and vast that we should expect to see evidence of at least some advanced civilizations. The numbers seem to support this conclusion absolutely. If only 1 in a billion star systems produces intelligent life, and if intelligent civilizations can persist for even just 10,000 years, then statistically, there should be millions or billions of advanced civilizations scattered throughout the galaxy alone. Furthermore, if even a fraction of these civilizations develop the technology for interstellar travel or communication, which seems inevitable given enough time and resources, we should observe unmistakable signs of their presence. We should detect their radio broadcasts, observe the industrial signatures of their megastructures, witness the propulsion signatures of their spacecraft traversing the void between stars, or at minimum receive intentional messages beamed across the cosmos by beings eager to establish contact with other intelligent species. Yet the silence persists, and this silence has generated numerous proposed explanations, each more troubling than the last, all of which highlight fundamental uncertainties about the nature of life, consciousness, and civilization. Some scientists propose the Great Filter hypothesis, suggesting that some incredibly rare event or condition exists somewhere along the pathway from non-living chemistry to advanced spacefaring civilization, and this event is so improbable that it essentially guarantees we are alone. Others propose that intelligent life is indeed common, but civilizations inevitably destroy themselves before achieving the technological capacity for interstellar communication or travel, suggesting that the development of nuclear weapons or artificial intelligence or other existential technologies is essentially incompatible with long-term survival. Still others speculate that perhaps advanced civilizations deliberately avoid contact with younger species, adhering to some unwritten cosmic code of non-interference, or that they simply find no value in communicating with us, treating younger civilizations as we might treat ant colonies, present but not worthy of interaction. Some theorists propose that intelligent life might develop in forms so utterly alien to our own that we would not recognize it as intelligent even if we encountered it directly, or that consciousness and civilization might be expressed in ways so fundamentally different from human experience that our search methods are intrinsically inadequate. What makes the Fermi Paradox genuinely unsettling is not merely the unanswered question itself, but rather how thoroughly we have normalized the profound absence of an answer despite its implications for our place in the universe. We continue conducting our ordinary lives, pursuing our daily concerns, without the emotional weight that this silence should perhaps impose upon us. We have developed frameworks and hypotheses to explain the paradox, converting the disturbing silence into an intellectual puzzle to be solved rather than a cosmic mystery that should fundamentally alter how we perceive our own significance and vulnerability. In 1935, a physicist named Erwin Schrödinger proposed a thought experiment that would come to haunt the foundations of quantum mechanics and expose a fundamental tension between the microscopic and macroscopic worlds. Schrödinger imagined a sealed box containing a living cat, a radioactive atom, a radiation detector, a hammer, and a vial of poison gas, all arranged in such a way that if the radioactive atom decays and is detected, the hammer would strike the vial and release the poison, killing the cat. The box is sealed and left undisturbed for 1 hour, during which the radioactive atom has a 50% chance of decaying. According to the principles of quantum mechanics, the atom exists in what is called a superposition, meaning it is simultaneously in both a decayed and undecayed state until the moment it is observed or measured. Therefore, if we follow quantum logic strictly, the cat inside the sealed box should also exist in a superposition of both alive and dead at the same time, remaining in this impossible state until someone opens the box and observes the contents, at which point the superposition collapses into a single reality. The psychological power of this paradox lies in its deliberate violation of our intuitive understanding of how reality functions. We know from lived experience that a cat cannot be both alive and dead simultaneously, that such a state is logically impossible and biologically nonsensical. A cat is a macroscopic object subject to the laws of classical physics, where particles have definite positions and velocities, where objects exist in single definite states independent of observation. Yet Schrödinger deliberately extended quantum principles, which do seem to apply accurately at the subatomic level, to this absurdly large and obviously impossible scenario. He was not actually proposing that cats exist in superposition, but rather using the paradox to illuminate a profound conceptual problem that quantum mechanics had created but failed to adequately address. The experiment forces us to confront the question of where exactly the quantum world ends and the classical world begins, and why the rules that govern electrons and photons seem to break down completely when applied to objects we can see and touch. The mechanism behind our acceptance of this paradox, our willingness to contemplate it seriously rather than dismiss it as obvious nonsense, stems from our deep respect for the mathematical framework of quantum mechanics, which has proven extraordinarily successful at predicting the behavior of subatomic particles. We have learned through decades of scientific education and popular science writing that quantum mechanics operates according to strange and counterintuitive principles, that observation affects reality, that uncertainty is fundamental to nature, and that superposition is a real phenomenon at the quantum scale. This knowledge creates a kind of cognitive flexibility in which we accept that the rules might be different at different scales, that reality might be fundamentally stranger than we assumed. When Schrödinger presents his thought experiment as a logical extension of accepted quantum principles, we feel compelled to take it seriously, to wrestle with its implications rather than simply declaring it impossible. The paradox gains its power not from any evidence that cats actually exist in superposition, but from the fact that our best physical theory seems to suggest they should, and we cannot find a completely satisfactory explanation for why they do not. What is remarkable is how this paradox has persisted as a central topic in discussions of quantum mechanics for nearly a century, despite the fact that most physicists acknowledge the thought experiment does not actually represent any genuine ambiguity about the real world. No competent physicist believes that a cat is actually both alive and dead before the box is opened. Many interpretations of quantum mechanics have been proposed to resolve the paradox, including the Copenhagen interpretation, the many worlds interpretation, objective collapse theories, and quantum decoherence approaches. Yet none has achieved universal acceptance, and the paradox remains unresolved. We have normalized this paradox to such a degree that it has become a cultural touchstone, referenced in popular media, used as a metaphor for indecision, discussed casually as though it represents a genuine mystery about the nature of reality. Yet fundamentally, it reveals not a paradox in nature itself, but rather a limitation in how we have chosen to apply quantum mechanical formalism to macroscopic systems, a mismatch between our mathematical theory and our physical intuitions that we have learned to live with rather than resolve, allowing Schrödinger's cat to exist in a state of perpetual superposition in our collective consciousness. Imagine for a moment that you are sitting alone in a vast, empty universe billions and billions of years in the future, long after all stars have burned out, long after all galaxies have dissipated into cold darkness, long after every structure of matter has decayed into its most fundamental particles scattered across an incomprehensibly vast expanse of space. In this infinitely distant future, the universe will reach what physicists call thermal equilibrium, a state of maximum entropy where nothing interesting can happen, where no energy gradients exist to do work or create change or sustain consciousness. Yet in this empty darkness, something truly peculiar becomes theoretically possible, something that seems to violate our most basic intuitions about how reality works. According to the mathematics of statistical mechanics and quantum fluctuations, there exists a non-zero probability, however extraordinarily tiny, that random particles could spontaneously assemble themselves into a conscious brain, fully formed and capable of thought, complete with false memories intact, emerging from pure chaos for just a brief moment before dissolving back into disorder. This is the Boltzmann Brain, named after the 19th-century Austrian physicist Ludwig Boltzmann, who first grappled with these unsettling implications of thermodynamic theory. The mechanism underlying this paradox rests upon a simple but profound principle in physics. If you wait long enough, if you allow an infinite amount of time to pass, then statistically speaking, virtually any configuration of matter becomes possible, no matter how improbable. The universe, in its random thermal fluctuations, will eventually produce every possible arrangement of particles that the laws of physics permit, given sufficient time. A conscious brain requires a very specific arrangement of atoms and molecules and synaptic connections, yet it is still just one possible configuration among countless others. The probability is vanishingly small, incomprehensibly microscopic, yet it is not zero. In an infinite universe over infinite time, even events with infinitesimal probability eventually occur. Furthermore, in the deeply weird landscape of quantum mechanics, virtual particles constantly appear and disappear from the quantum vacuum itself, and these fluctuations could, in principle, randomly assemble into macroscopic objects. So if we accept these premises of physics, then the conclusion seems inescapable. Boltzmann brains must eventually come into existence through pure random chance, spontaneously emerging from the void, thinking thoughts and experiencing moments of consciousness before entropy claims them once again and scatters them back into disorder. This creates what physicists call the Boltzmann brain problem, a paradox that strikes at the heart of cosmology and what we understand about the nature of consciousness and reality itself. The problem unfolds like this. If Boltzmann brains are genuinely possible outcomes of physical law, and if infinite time and space exist, then statistically speaking, there should be vastly more Boltzmann brains existing throughout the universe than actual brains like yours that arose through biological evolution. The numbers are so staggeringly lopsided that it seems most conscious observers should be Boltzmann brains, not evolved beings like humanity. Yet here you are, apparently an evolved brain with genuine continuity and real memories, rather than a spontaneous fluctuation with implanted false memories. This contradiction suggests something may be fundamentally wrong with our understanding of cosmology, thermodynamics, the nature of consciousness itself, or perhaps even the basic structure of reality. The paradox persists in modern physics despite its troubling implications because it emerges inevitably from mathematical frameworks that have proven extraordinarily successful in explaining the universe. Scientists cannot simply dismiss it or pretend it does not exist, yet neither can they resolve it completely. Various theoretical solutions have been proposed. Perhaps the universe is not infinite in size or infinite in duration, which would eliminate the problem by making Boltzmann brains truly impossible rather than merely improbable. Perhaps quantum mechanics functions in ways we do not yet fully understand, preventing the assembly of macroscopic objects from pure fluctuation. Perhaps consciousness itself is something fundamentally different from physical brain states, something that cannot spontaneously arise from random particles. Or perhaps we live in a universe with special initial conditions that strongly suppress entropy and Boltzmann brain formation, a possibility that raises its own questions about cosmic origins and fine-tuning. Imagine holding a solid sphere in your hands, a perfectly uniform ball of matter with a defined boundary and consistent density throughout. Now imagine that through a series of carefully constructed mathematical operations, you could separate this sphere into a finite number of non-overlapping pieces, and then reassemble those exact same pieces using only rotations and translations through space, with no stretching or deformation, to create two identical spheres, each with the same size, shape, and volume as the original. This is the essence of the Banach-Tarski Paradox, one of the most counterintuitive and philosophically troubling results in modern mathematics, discovered in 1924 by Stefan Banach and Alfred Tarski, though the implications were not fully appreciated until decades later when mathematicians began to grapple with its deeper meaning and its relationship to the nature of infinity, dimensionality, and physical reality itself. The mechanism underlying this paradox lies in the properties of infinite sets and the behavior of rotations in three-dimensional space, specifically in how we define what constitutes a piece or a part of an object when dealing with mathematical abstractions rather than physical materials. The decomposition does not work by cutting the sphere into a finite number of ordinary pieces, the way you might slice an apple with a knife to create discrete chunks with well-defined boundaries. Instead, the pieces involved in the Banach-Tarski decomposition are extraordinarily complex, infinitely intricate sets of points scattered throughout the sphere in a manner so elaborate that they defy intuitive visualization or physical realization. These pieces are not simply disconnected from one another, but rather they interweave and interpenetrate in ways that have no analog in the physical world, existing only in the realm of pure mathematical abstraction where sets can be infinitely fragmented and still possess measurable properties. The mathematical machinery that makes this possible relies on the axiom of choice, a foundational principle in set theory that allows mathematicians to select elements from infinitely many sets simultaneously, even when no explicit rule or algorithm can describe which elements are being chosen. What makes the Banach-Tarski paradox so deeply unsettling is that it demonstrates a fundamental disconnect between mathematical possibility and physical reality, suggesting that our intuitions about space, volume, and conservation of matter, intuitions honed by millennia of evolutionary adaptation to macroscopic physical phenomena, break down entirely when we venture into the abstract realm of pure mathematics and infinite sets. The pieces in the decomposition cannot be assembled in any physically realizable way, as they exist only as theoretical constructs, yet the mathematical proof is logically sound and incontrovertible within the axioms of standard set theory, meaning that the paradox persists not because mathematicians have made an error, but because the structure of mathematics itself, when extended to infinite sets, permits possibilities that seem to violate our most basic assumptions about how the world works. We have come to accept this strange result as a permanent fixture of mathematical knowledge, a reminder that infinity operates according to principles fundamentally alien to finite human experience, and that the universe of pure mathematics contains truths that are logically valid but physically impossible. Forever separating the abstract intellectual realm from the concrete material world, we inhabit and navigate with our everyday intuitions about volume, conservation, and the boundaries between distinct objects. Imagine a scenario in which a person becomes aware of a future event through some means, perhaps a prophecy, a vision, a warning from a time traveler, or an extraordinarily accurate prediction. And this knowledge of the future event becomes the very catalyst that causes that event to occur in the first place, creating a self-fulfilling loop that appears to trap reality in an inescapable circle of causation. The predestination paradox emerges when someone learns what is supposed to happen to them or around them, and in their attempt either to prevent it or to ensure it comes to pass, they inadvertently become the architect of their own fate, making the prophecy or prediction true through the very actions they take in response to learning about it. This is distinct from other time travel paradoxes because it does not necessarily require actual time travel at all, though time travel scenarios often illustrate it most clearly. The paradox becomes most apparent when we consider that the person's knowledge of the future, combined with their rational response to that knowledge, creates a causal chain that was entirely absent before they became aware of the prediction. Yet somehow this chain was always supposed to happen, suggesting that the future reached backward through time to influence present action and create itself retroactively. Consider the classical example often drawn from mythology and ancient literature, the case of Oedipus, who is told by the oracle that he will kill his father and marry his mother, a prophecy so horrifying that he attempts to escape it by fleeing his home and the people he believes to be his parents, yet through a series of events set in motion by his desperate flight, he encounters and kills a stranger on the road who was actually his biological father, and later marries the widow of that man, who is his biological mother, thereby fulfilling the prophecy through his very attempt to avoid it. The mechanism here is that Oedipus's knowledge of the prediction changes his behavior in ways that directly enable the prophecy to come true, suggesting that if he had never been told the prophecy, he would have lived a normal life with his actual parents and never fulfilled it at all. The future event, in other words, appears to have caused itself by first causing Oedipus to learn about it, which caused him to act in ways that made it inevitable. The logical problem emerges when we ask whether the prophecy was truly inevitable from the beginning, or whether the act of telling Oedipus the prophecy created the inevitability, which would mean the future did not predetermine the past, but rather the knowledge of an imagined future altered present behavior to create that future retroactively. The psychological mechanism that sustains the predestination paradox involves the human mind's tendency to interpret information as confirmation of an already determined fate once we become aware that something supposedly must happen to us. When a person learns of a prediction, they often become hypervigilant to signs that the prediction is coming true. They interpret ambiguous events as confirmation of the prophecy, and they may unconsciously guide their own decision-making toward outcomes that align with the prediction, not out of mystical compulsion, but simply because the prediction has been integrated into their worldview and their sense of what is likely or possible. A person told they will fail at a particular task often becomes more anxious about that task. Their anxiety impairs their performance, and they fail not because the prediction was true from the start, but because the prediction created the psychological conditions for failure. A person warned that someone will betray them may become suspicious, may interpret neutral actions as evidence of betrayal, may withdraw trust preemptively, and may thereby create the very betrayal they feared by treating the other person with unfounded hostility. The prediction becomes true not because it was ever written in the stars, but because the human being who learned of the prediction altered their cognition, their perception, and their behavior in response to the information. And these alterations created the very outcome that was supposedly predetermined. This paradox persists in our modern consciousness despite our rational understanding of causation, and it does so partly because human beings have a fundamental difficulty reasoning clearly about situations in which knowledge of a future event might change the present in ways that create that event. We find ourselves trapped in a conceptual loop where we cannot decide whether the prophecy caused the action or the action caused the prophecy. And this confusion mirrors the confusion between correlation and causation that affects much of human thinking. Imagine you are standing at one end of a room and you wish to walk to the opposite wall. Before you can reach that wall, you must first travel half the distance to it. But before you can travel that half distance, you must first travel half of that distance, and then half of that distance, and then half of that distance again, continuing infinitely into smaller and smaller increments. Since you must complete an infinite number of these smaller journeys before you can complete even one journey across the room, and since it is logically impossible to complete an infinite sequence of actions in a finite amount of time, you should theoretically never be able to reach the wall at all. Yet every day, billions of people walk across rooms, travel down hallways, drive cars, and move through space with complete ease, apparently solving this paradox without effort or concern. This is Zeno's paradox of motion, proposed by the ancient Greek philosopher Zeno of Allais around 2,500 years ago, and it remains one of the most perplexing logical challenges to our fundamental understanding of movement, time, and infinity. The real-life situation that Zeno describes is remarkably simple and utterly commonplace. Every moment that we move through physical space, we are apparently encountering the mathematical structure that his paradox identifies. When you walk from your bedroom to your kitchen, you traverse an infinite number of infinitesimal distances. When a car drives down a highway, it must cover half the remaining distance to its destination infinite times. When you reach toward an object, your hand must complete an infinite number of movements before it touches that object. The paradox seems to apply to every single instance of motion that occurs in our universe, from the flight of an arrow to the orbit of planets to the expansion of the cosmos itself. The logical framework that Zeno constructed appears to be describing something real and unavoidable about the nature of physical space and movement through it. Yet we observe motion happening constantly, everywhere, all the time, without any apparent contradiction or violation of the laws of physics. This fundamental disconnect between what logic seems to demand and what our eyes and experience tell us is real creates a profound cognitive dissonance. The psychological and logical mechanism behind Zeno's paradox operates through a clever manipulation of our intuitions about infinity and completion. Zeno forces us to accept two seemingly self-evident propositions. First, that space and time can be divided infinitely, broken down into smaller and smaller segments without limit. And second, that to complete a journey, you must actually complete every single one of these infinite segments, one after another, in sequence. From these two premises, the conclusion that motion is impossible logically follows with remarkable force. Our minds can grasp the idea of infinity in the abstract, but we struggle profoundly when we try to imagine actually completing an infinite number of tasks, actually finishing an infinite sequence of actions. The paradox exploits this gap between our abstract understanding and our intuitive grasp. Additionally, Zeno's argument seems to rest on the assumption that infinite sums cannot be finite, that adding together infinitely many positive quantities must always result in infinity. This intuition feels correct and even obvious, yet it is precisely this assumption that mathematics would later overturn. The paradox persists through a kind of conceptual sleight of hand, where we accept unexamined premises that feel true, but which lead us to absurd conclusions about a world that clearly works fine. Over the centuries, mathematicians and philosophers have approached Zeno's paradox from multiple angles, yet the paradox continues to fascinate precisely because it highlights genuine tensions in how we conceptualize reality. The mathematical resolution came through calculus and the study of infinite series, which revealed that under certain conditions, an infinite sum of progressively smaller quantities can indeed converge to a finite value. The series 1/2 plus 1/4 plus 1/8 plus 1/16, continuing infinitely, actually equals exactly 1. This mathematical insight directly undermines Zeno's reasoning, yet the paradox remains philosophically intriguing because it touches on deeper questions about the nature of time, causation, and the relationship between the mathematical description of reality and reality itself. We have essentially normalized this paradox by accepting that the real world operates according to physical laws that permit motion, and we trust our mathematical and scientific frameworks to explain how this occurs. Yet the basic tension that Zeno identified remains present in the background of our understanding, a reminder that infinity and motion are concepts more subtle and complex than our Eve. Imagine two identical twins standing together on Earth, holding hands, knowing that they will soon be separated not by distance alone, but by the very fabric of time itself. One twin, let us call her Alice, will board a spacecraft capable of traveling at nearly the speed of light, while her sister Betty remains behind on Earth, watching from the ground as the ship accelerates into the darkness of space. According to the predictions of Einstein's theory of special relativity, something profoundly strange will occur during this journey, something that seems to violate our most fundamental understanding of fairness and symmetry in the universe. When Alice returns to Earth after her voyage, having traveled for what feels like only a few years from her perspective, she will discover that her twin sister Betty has aged far more dramatically, perhaps by decades, while Alice herself has barely aged at all. The twin who traveled through space at relativistic speeds will be younger than the twin who remained stationary on Earth, and this difference will be permanent and measurable and utterly real, not merely an illusion of perception or a trick of measurement. This is the twin paradox, and it emerges from one of the most counterintuitive consequences of special relativity, the phenomenon known as time dilation. The mechanism underlying this paradox rests on a principle that Einstein revealed to us more than a century ago, a principle that still seems to defy common sense even as we acknowledge its mathematical validity. According to special relativity, time does not flow at a constant rate for all observers. Instead, the rate at which time passes is relative to the observer's state of motion through space. For an object moving at high velocity relative to a stationary observer, time itself slows down. This is not a metaphorical slowing. It is a literal reduction in the rate at which time elapses for the moving object as measured by the stationary observer. The faster an object moves through space, the slower time passes for that object, and this effect becomes increasingly pronounced as velocities approach the speed of light. So when Alice travels at 99% of light speed, time for her does indeed slow down dramatically compared to time for Betty on Earth. Alice's heart beats more slowly from Betty's perspective, her cells divide more slowly, her entire biological and physical processes unfold at a reduced rate. For Alice, subjectively, everything feels normal. Her clock ticks at what seems like its usual rate, her body ages as it always has, but from Betty's vantage point on Earth, Alice is moving through time in slow motion. The paradox itself arises from a seemingly logical objection to this explanation, an objection that troubled physicists when the implications of special relativity first became clear. If motion is relative, as Einstein insisted, then from Alice's perspective during the journey, it is Betty who is moving away at high velocity, not Alice herself. By this reasoning, from Alice's frame of reference, it should be Betty whose time is slowing down, which would mean that Betty should age more slowly than Alice, the opposite of what the theory predicts. So which twin actually ages more slowly? How can both perspectives be correct when they lead to opposite conclusions? The resolution to this apparent contradiction lies in understanding that the situation is not, in fact, symmetrical. Alice must accelerate and decelerate at the beginning and end of her journey, while Betty remains in a single inertial reference frame the entire time. This acceleration breaks the symmetry between the two twins. While special relativity applies to observers in constant relative motion, the accelerating twin occupies a special role, and the laws of physics, when properly applied, predict that the accelerating twin will be younger upon return. General relativity provides an even more complete explanation. Acceleration is indistinguishable from gravity, and in a gravitational field, time passes at different rates for objects at different positions, with time passing more slowly in stronger gravitational fields. What makes the twin paradox so persistent in our collective consciousness, despite its complete resolution through well-established physics, is that it touches something deeper than mere mathematical confusion. It presents a scenario that our intuition, shaped by everyday experience, finds genuinely repugnant. We have evolved to understand time as universal and absolute, the same for everyone everywhere, a river that flows at the same speed regardless of where you stand on its banks. The notion that time itself can literally pass at different rates for different observers, that one person can objectively age less than another person who was born at the same moment, challenges the bedrock assumptions upon which we construct our sense of reality. Imagine a book burning in a fire, its pages curling and blackening until nothing remains but ash and smoke, and consider what modern physics tells us must be true about that moment. According to the laws of thermodynamics and quantum mechanics, every piece of information contained within those pages, every word and every idea and every pattern of ink upon paper, must somehow still exist somewhere in the universe in some form, encoded perhaps in the heat and radiation and the specific arrangement of ash particles. Yet we have no practical way to recover it and no technology that could ever reconstruct the original text from the charred remains scattered by the wind. This is the information paradox at its heart, a collision between what the universe appears to allow and what our best theories of physics insist must be true, and it represents one of the deepest unsolved problems in theoretical physics, particularly when considering what happens at the edge of black holes, where the paradox becomes even more acute and troubling. The paradox emerges most starkly when we consider black holes, those regions of spacetime so densely packed with matter that not even light can escape their gravitational pull. Because Stephen Hawking discovered in 1974 that black holes are not entirely black, but rather emit radiation due to quantum effects near the event horizon, and this radiation carries away energy, causing the black hole to slowly evaporate over vast periods of time, shrinking gradually until it disappears completely. The problem is that when a black hole evaporates entirely, all the information about everything that fell into it seems to vanish from the universe completely, and this appears to violate a fundamental principle of quantum mechanics called unitarity, which states that information cannot be created or destroyed, but only transformed and rearranged, meaning that in a deterministic universe operating under quantum rules, if you know the complete state of a system at one moment in time, you must in principle be able to calculate its complete state at any other moment in time, past or future. Yet with black holes this seems impossible, because once matter crosses the event horizon and falls into the black hole, we cannot observe what happens to it, and when the black hole evaporates, the information appears to be permanently lost, leaving us with a fundamental question about whether the laws of physics as we understand them are truly reversible and deterministic at the deepest level, or whether information is genuinely destroyed in the universe, which would represent a catastrophic failure of quantum mechanics itself. The psychological and conceptual mechanism behind why this paradox persists is rooted in the collision between two pillars of modern physics that have never been successfully reconciled: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles and atoms at microscopic scales. General relativity, developed by Einstein, treats spacetime as a smooth, continuous fabric that can bend and curve, and it makes no inherent provision for quantum effects or information preservation at the singularities found at the centers of black holes, where the equations break down completely. Quantum mechanics, on the other hand, is fundamentally information-preserving and time-reversible, operating under the mathematical framework of unitary evolution, where every state contains complete information about all states that came before it and all states that will come after it. When we try to apply quantum mechanics to black holes, we must grapple with the fact that general relativity seems to allow information to be destroyed, while quantum mechanics insists it cannot be, creating a logical contradiction that suggests our understanding of at least one of these theories, and possibly both, is incomplete or incorrect at extreme densities and temperatures. Physicists have proposed various potential resolutions to this paradox, including the holographic principle, which suggests that all the information about the interior of a black hole might be encoded on its surface in a way we have not yet learned to read, or the idea that information is not actually lost, but somehow preserved in subtle correlations in the Hawking radiation that we are currently unable to detect or measure. Others have suggested that black holes do not actually evaporate completely, but leave behind small remnants containing all the information, or that the information escapes through wormholes into other universes, or that the very concept of information loss requires a revision of quantum mechanics itself to allow for non-unitary processes. Imagine standing in a vast, endless forest on a perfectly clear night, and you gaze upward at the sky above you. According to the most straightforward interpretation of what an infinite universe should look like, every single direction your eyes travel should eventually land upon a star, because if the universe extends infinitely in all directions and contains an infinite number of stars distributed throughout that infinite space, then logically there should be no gaps, no darkness, no void between the celestial bodies. Yet when you actually look up at the night sky, as we have done for thousands of years of human observation, you see predominantly darkness punctuated by scattered points of light, a cosmic emptiness that seems to contradict what pure mathematics and logic would predict. This is Olbers Paradox, named after the 19th century German astronomer Heinrich Olbers, who articulated it clearly, though the question had troubled thinkers since at least the time of Thomas Digges in the 16th century, and it remains one of the most elegant demonstrations of how our intuitive understanding of infinity can completely fail to match observable reality. The psychological and logical mechanism at work here stems from how we naturally extrapolate from finite experience into infinite domains. When we think about an infinite universe filled with an infinite number of stars, our minds tend to apply the same proportional reasoning that works in finite contexts, imagining simply scaling up our local astronomical neighborhood forever in all directions. We imagine that if the universe is infinite and stars are distributed throughout it at some consistent density, then looking in any direction should eventually hit a star, and the total brightness from all these stars should be overwhelming, should turn the entire night sky into a blazing continuous light source, brighter than the daytime sun. Our intuitive sense of how infinity works suggests that more plus more plus more, infinitely, must equal everything, must fill everything completely, must leave no room for darkness. This reasoning seems airtight, seems inevitable, seems like the only logical conclusion possible when you state the premises clearly. And yet the night sky remains dark, remains punctuated with stars rather than entirely filled with stellar light, and this contradiction creates a genuine puzzle that demands explanation rather than dismissal. What resolves this paradox? What explains why the night sky is dark despite living in an apparently infinite universe involves multiple mechanisms working together in complex interplay. The universe we have discovered through modern cosmology and physics is not infinite in age, having instead a definite beginning approximately 13.8 billion years ago in what we call the Big Bang, which means that light from the most distant regions of the universe simply has not yet had time to reach us, no matter how far those regions might be, creating a practical horizon beyond which we cannot see. Additionally, the universe is expanding, and space itself is stretching at an accelerating rate, which means that the light from distant galaxies is progressively redshifted to longer wavelengths, losing energy and becoming dimmer as the space between us and those sources expands, effectively removing their contribution to the brightness of the night sky. Furthermore, dust and gas in space absorb and scatter light, creating opacity over cosmic distances that prevents the light from reaching us even when it was originally emitted. And even setting all these complications aside, the inverse square law of physics dictates that light spreads out and weakens with distance in a way that actually prevents an infinite concentration of brightness despite infinite numbers of sources. These explanations, when properly worked through with rigorous mathematics, completely account for the darkness of the night sky and eliminate any genuine contradiction between theory and observation. Yet what is fascinating about Olbers' paradox is how it persists in human consciousness despite being thoroughly solved and explained scientifically, how it continues to provoke wonder and contemplation even among those who understand the technical resolutions completely. It endures because it touches something fundamental about how we relate to infinity, how we struggle to intuitively grasp scales and magnitudes that exceed our evolutionary experience, how mathematics can lead us toward conclusions that seem inescapable until they collide with reality and force us to reconsider our most basic assumptions about the structure of existence. The paradox reminds us that the universe is far stranger and more subtle than naive extrapolation can ever reveal, that infinity does not behave the way finite minds instinctively expect it to behave, and that the dark night sky, far from being empty or disappointing, is instead a pro. Imagine standing in front of a pile of sand on a beach, and someone asks you a deceptively simple question: how many grains of sand does it take to make a heap? You might reasonably answer that a single grain of sand is not a heap, and most people would agree with you on that fundamental point. Now imagine that same person adds 1 grain of sand to your pile and asks again, is this now a heap? 2 grains still does not seem like a heap, and you would likely say no. They continue this process, adding 1 grain at a time, asking the same question repeatedly. At what precise point does your pile transform from not being a heap into being a heap? This is the essence of the Sorites Paradox, a logical puzzle that has haunted philosophers for over 2,000 years, and it reveals something profound about the way language, perception, and logic interact in the human mind. The paradox emerges from what logicians call a Sorites series, a sequence of small, incremental changes where each individual step seems negligible and insignificant. The reasoning appears airtight at first glance. If 1 grain of sand is not a heap, and adding a single grain to a non-heap cannot create a heap because 1 grain makes no meaningful difference, then by this logic, no amount of sand, no matter how much you accumulate, could ever become a heap. This leads to an absurd conclusion that contradicts our everyday experience and common sense. Yet the chain of reasoning that gets us there seems impossible to break at any single point along the way. The psychological mechanism that makes the Sorites paradox so persistently troubling relates to how our minds handle boundary conditions and categorical distinctions. We naturally organize the world into discrete categories: heap and non-heap, bald and not bald, rich and poor, young and old. These categories feel like they have clear, definable borders, and our language reinforces this illusion by treating them as binary states rather than continuous spectrums. However, reality often presents us with gradual transitions rather than sharp cutoffs, and our cognitive systems struggle to reconcile this fundamental mismatch between how we perceive discrete categories and how the world actually transitions between different states. What makes this paradox particularly fascinating is that it is not actually a flaw in logic itself, but rather a flaw in how we attempt to apply rigid logical categories to inherently fuzzy phenomena. The Sorites paradox exposes a deep tension between classical logic, which demands that any proposition must be either true or false with no middle ground, and the way the natural world actually works, where many qualities exist on a continuum. Our language evolved to describe physical reality, and it developed vague predicates because vagueness is actually more useful for navigating a complex, continuous world than absolute precision would be. Throughout the centuries, philosophers have proposed various solutions to this paradox, each with its own compelling arguments and troubling implications. Some suggest that there simply must be a precise cutoff point, even if we cannot identify it, and that our inability to pinpoint it reflects only the limitations of human knowledge rather than any genuine logical problem. Others argue that we should abandon classical logic altogether and adopt a fuzzy logic system where propositions can have degrees of truth rather than being absolutely true or false. Still, other philosophers contend that the paradox reveals a fundamental vagueness in our language itself, meaning that the word heap simply does not have a precise definition, and asking where it begins is like asking where red ends and orange begins in the spectrum of visible light. The remarkable thing about how we have normalized the Sorites paradox in our everyday lives is that we simply accept vagueness without complaint. We know that there is no clear line between youth and middle age, between poverty and modest means, between being awake and being asleep, yet we continue to use these categories as though they were perfectly well defined. Our legal systems draw arbitrary lines that make something illegal at one moment and legal the next based on age, income, or intoxication levels, despite knowing intellectually that these categories are fundamentally vague. We have built societies and entire institutional frameworks around categorical distinctions that the Sorites paradox proves cannot be logically justified in any absolute sense. And yet everything functions reasonably well because we have collectively agreed to pretend that these boundaries are real and meaningful even when they are ultimately constructed and conventional. In the late 19th century, a mathematician named Bertrand Russell discovered something that would shake the very foundations of logic and set theory. A discovery so troubling that it revealed a fundamental contradiction lurking within the heart of mathematics itself. A contradiction that had gone unnoticed for decades as mathematicians built increasingly complex structures on what they believed to be solid ground. Russell's paradox emerges from what seems like a simple and innocent question, one that appears to require no more than a moment of logical reflection to answer. Yet when examined closely, it opens into an abyss of self-reference and contradiction that challenges our most basic assumptions about how categories and classifications can be organized. The paradox begins with the concept of sets, which mathematicians use as the fundamental building blocks of their discipline, containers that hold objects or other sets, organized according to rules that should be perfectly clear and rational. We might have a set of all red apples, or a set of all numbers greater than 5, or a set of all chairs in a particular room, and these sets seem unproblematic because they follow a logical principle of membership based on some defining characteristic. However, Russell asked a question that conventional mathematics had never properly addressed. What about sets that contain themselves as members, sets that are self-referential in their very definition? He imagined a set defined as the collection of all sets that do not contain themselves, a seemingly straightforward concept, and then he asked whether this particular set should contain itself as a member or not. If the set contains itself, then by definition it should not contain itself, because it is defined as containing only those sets that do not contain themselves. But if the set does not contain itself, then by the very definition it should contain itself, because it is a set that does not contain itself. This circular logic, this impossible contradiction, revealed that something fundamental was wrong with the mathematical framework that had been taken for granted. The psychological mechanism that allowed this paradox to remain hidden for so long relates to the human tendency to construct increasingly abstract systems without regularly examining their foundational assumptions, a tendency that affects mathematicians and philosophers just as it affects all of us in our daily thinking. We build elaborate structures of logic and classification, assuming that the base upon which we stand is solid, and we rarely pause to question whether the very concept of membership and self-reference might contain hidden contradictions. Russell's work forced mathematicians to confront the fact that their entire discipline was built on definitions and axioms that had never been rigorously scrutinized, that the intuitive notion of what a set is and what it means to contain something had been assumed rather than proven. The discovery created a crisis in mathematics known as the foundational crisis, prompting logicians to develop more careful systems like axiomatic set theory, which restricts how sets can be formed and explicitly prohibits the kind of self-referential definitions that lead to Russell's paradox. Yet despite these careful reconstructions and these new foundations, the paradox itself persists as a reminder of something profound about language, logic, and self-reference, something that cannot be entirely eliminated through formal definitions. The paradox demonstrates that certain questions about the nature of categories and membership, questions that seem perfectly reasonable in ordinary language, can lead to unavoidable contradictions if we are not careful about how we structure our definitions. We have learned to work around this problem by accepting constraints on what kinds of sets we allow, by establishing hierarchies of types so that a set cannot contain itself in problematic ways, by building in safeguards that prevent the kind of circular reasoning that generates the paradox. Yet the paradox remains psychologically and philosophically unsettling because it suggests that something about the way human thought naturally categorizes and organizes information contains this potential for self-contradiction, that the mind's tendency to create increasingly abstract and self-referential systems may be intrinsically vulnerable to paradox. Russell's paradox has never been solved in the sense of being eliminated or explained away, but rather it has been managed and contained through careful logical architecture, which perhaps is the best we can hope for when confronting the deepest logical structures of reality and thought themselves. Imagine you are presented with two boxes, and you are told that a highly intelligent predictor, one with an almost perfect track record of accurately foreseeing human behavior, has already made a prediction about what you will do in this very moment. Box A contains $1,000, a modest sum, but real money nonetheless. Box B contains either $1 million or absolutely nothing, and the predictor's choice about what goes into Box B depends entirely on what the predictor believes you will do right now. If the predictor thinks you will take both boxes, then Box B contains nothing, and you will walk away with only the $1,000 from Box A. However, if the predictor believes you will take only Box B and leave Box A behind, then Box B contains $1 million and you will become substantially wealthier. You must now make your choice, knowing that the predictor has already completed their analysis and placed the money accordingly. The question that haunts this scenario is deceptively simple. Should you take both boxes, or should you take only box B? The logical tension here emerges from a collision between two compelling but contradictory lines of reasoning. From one perspective, the predictor has already made their decision and placed money in the boxes before you choose. Whatever you decide to do now, the contents of the boxes are already fixed and determined. Therefore, if you take both boxes, you get $1,000 plus whatever is in box B, which is already decided. If you take only box B, you still get whatever is already in box B. This means taking both boxes strictly dominates taking only one box, because you receive everything in box B regardless, plus you get the additional $1,000 from box A. This reasoning suggests that rational self-interest demands you take both boxes. Yet there exists an entirely different logical framework that contradicts this conclusion. The predictor is known to be extraordinarily accurate at predicting human choices, which means there is a powerful statistical correlation between what the predictor predicted and what you actually do. The predictor predicted that people who reason through this scenario in a self-interested way, people who see the boxes as already filled and therefore conclude they should take both, will indeed take both boxes. But the predictor also predicted that people who reason in a more consequentialist way, people who recognize that their choice is correlated with the predictor's prediction, will take only box B. In other words, if you decide to take both boxes, you are implicitly confirming the predictor's expectation that you would think and reason exactly this way, which means you will likely find box B empty. Conversely, if you resist the apparently logical conclusion and take only box B, you are aligning your behavior with what the predictor expected of someone who would make such a choice, which means box B probably contains $1 million. This reasoning suggests you should take only box B. What makes Newcomb's paradox so intellectually vexing is that both lines of reasoning appear sound, yet they lead to opposite conclusions. Philosophers and decision theorists have argued passionately about this problem for decades without reaching universal consensus. Some argue that the causal structure of the situation is what matters most, pointing out that your present choice cannot causally affect what the predictor has already done, making the both boxes choice the only rationally defensible position. Others argue that correlation and prediction can matter just as much as causation in decision-making, and that ignoring the predictor's accuracy is a form of irrational overconfidence. Still others suggest the paradox reveals a fundamental confusion about what we mean by rational action, or whether rational action is even possible in situations where our choices are predicted or determined by prior conditions. The persistence of Newcomb's paradox in philosophical discourse reveals something profound about human reasoning and decision-making under uncertainty. We have built entire systems of logic and economics around the assumption that rational actors should always choose to maximize their immediate payoff. Yet Newcomb's scenario demonstrates that this principle can lead to worse outcomes when our choices are correlated with outside predictions or events. The paradox exposes the difference between what we might call logical consistency and practical wisdom, between the rules we think should govern rational behavior and the actual consequences that follow from different choices. Rather than being resolved through clever argumentation, Newcomb's paradox has instead become a recurring point of reflection for anyone grappling with questions about free will, prediction, causation, and what rationality truly means when the future is not entirely open, but instead shaped by patterns that observer. Imagine yourself standing on the set of a game show called Let's Make a Deal, which aired from 1963 to the present day, hosted for many decades by a man named Monty, whose name would eventually become permanently attached to one of the most bewildering probability paradoxes in all of mathematics and human decision-making. You are presented with 3 doors, and behind one of these doors sits a brand new automobile, a prize of significant monetary value that would genuinely change your life if you were to win it. Behind the other 2 doors are consolation prizes, typically goats in modern retellings of this problem, though in the actual show they were far less glamorous items of negligible worth. You are asked to choose one door, and you select door number 1, committing to it without opening it, your hand resting on the cool metal handle as your heart quickens with the possibility of fortune. Now comes the crucial moment that makes this scenario so profoundly strange and counterintuitive to human reasoning. Monty, who knows exactly what is behind every single door, having complete and perfect information that you, as the contestant, do not possess, deliberately opens one of the other two doors that you did not choose, revealing one of the goats behind it. He then turns to you and asks a question that seems simple, but contains within it a mathematical trap that has confounded millions of people, including many who hold advanced degrees in mathematics and logic. Would you like to stick with your original choice of door number 1, or would you like to switch your selection to the one remaining unopened door? This is where the paradox reveals itself, because the correct answer, according to probability theory and rigorous mathematical analysis, is that you should absolutely switch your door choice, as doing so gives you a 2/3 chance of winning the car, whereas staying with your original choice gives you only a 1/3 chance. This conclusion seems to violate everything that human intuition tells us about how probability should work, because it feels as though, once Monty opens a door and reveals a goat, the remaining two unopened doors should each have an equal 50-50 chance of containing the automobile, making it irrelevant whether you switch or stay. The mechanism that underlies this counterintuitive result lies in the crucial detail that Monty Hall's action is not random, but rather deliberately informed by his complete knowledge of what is behind each door. When you initially chose door number 1, you had a 1/3 probability of having selected the door with the car and a 2/3 probability of having selected a door with a goat behind it. Those odds do not change when Monty opens a door, because Monty cannot open the door you chose, and he will always deliberately open a door that contains a goat. If your original choice was a goat, which happens in 2 out of every 3 scenarios on average, then the car must be behind the remaining unopened door, and Monty will open the other goat door. If your original choice was the car, which happens in only 1 out of every 3 scenarios, then Monty can open either of the 2 remaining doors, both of which contain goats, and the car will not be behind the remaining unopened door. By switching, you are essentially transferring your selection to whichever door Monty did not open and you did not choose, which means you are now betting on the 2/3 scenario where your original choice was incorrect. The mathematics is elegant and unambiguous once understood, yet it persists as a source of genuine confusion and resistance, even among people who have studied probability extensively. What makes the Monty Hall problem so philosophically fascinating is not merely that it is counterintuitive, but rather that it exposes a fundamental flaw in how human minds process information and evaluate conditional probability under conditions of uncertainty. Most people, when confronted with this scenario, experience a powerful psychological resistance to switching, because they perceive the situation after Monty opens the door as being fundamentally equivalent to a fresh, simple choice between 2 remaining doors, each of which should logically have equal odds of containing the prize. This perception is cognitively natural and deeply persuasive, yet it is precisely wrong in a way that mathematics can prove with absolute certainty. The problem has been tested countless times, explained in numerous different ways, published in mainstream newspapers and magazines, debated by mathematicians and statisticians, yet it continues to baffle people not because the explanation is unclear, but because the human mind struggles to internalize the idea that information asymmetry and selective revelation can alter probability in ways that feel counterintuitive. Consider the strange inversion at the heart of artificial intelligence and cognitive science, an observation so counterintuitive that it challenges nearly everything we believe about the nature of difficulty itself. Hans Moravec, a roboticist and artificial intelligence researcher, noticed something peculiar in the 1980s that continues to perplex and fascinate those who study machine learning and human cognition. He observed that tasks which seem extraordinarily difficult for computers are often trivial for humans, yet conversely, tasks that appear deceptively simple for humans prove to be remarkably difficult for machines to accomplish. A chess-playing computer can defeat the world's greatest human champions, calculating millions of positions per second and demonstrating a mastery of the game that seems almost superhuman in its precision and depth. Yet that same computer cannot reliably identify a cat in a photograph with the consistency that a 5-year-old child achieves effortlessly. A machine can perform complex mathematical calculations, solve abstract logic puzzles, and manipulate symbols with perfect accuracy, but it struggles to navigate a cluttered room, recognize facial expressions, or understand the emotional subtext of a casual conversation between friends. This paradox reveals something fundamental about the difference between conscious reasoning and the unconscious competencies that evolution has embedded into our species over millions of years. The mechanism underlying this paradox rests upon a profound asymmetry in the development of human intelligence and the nature of artificial reasoning. The skills that humans find effortless are precisely those that have been refined through evolutionary pressure for millions of years, encoded into our neural architecture through countless generations of survival and reproduction. Visual recognition, spatial awareness, the interpretation of social cues, and the coordination of physical movement through space are not abstract problems that we learn to solve through explicit reasoning. Rather, they are deeply ingrained capacities that operate beneath the threshold of conscious deliberation. When you recognize a friend's face in a crowded room, you are not performing a systematic analysis of pixel patterns or calculating geometric relationships between facial features. Instead, you are drawing upon billions of years of evolutionary refinement that has produced visual processing systems of extraordinary sophistication. By contrast, chess or formal logic are recent inventions in evolutionary terms, appearing only within the last few thousand years or less. These domains are governed by explicit rules that can be formulated mathematically and manipulated algorithmically, making them naturally suited to the kind of step-by-step logical processing that machines excel at performing. The paradox persists because we persistently misjudge the nature of difficulty itself, conflating computational complexity with practical challenge in ways that obscure the true structure of intelligent behavior. We have constructed a particular narrative about intelligence that privileges abstract reasoning, mathematical prowess, and logical manipulation as the highest forms of intellectual achievement, while treating sensory perception, physical coordination, and social understanding as somehow more primitive or less intellectually demanding. Yet the evolutionary record suggests the opposite ordering entirely. The cognitive unconscious, that vast realm of processing that occurs outside of awareness and deliberate calculation, has proven far more challenging to replicate in machines than any amount of abstract reasoning. We have created systems capable of defeating world champions in games that once seemed to epitomize human intellectual superiority, yet we have not created anything that can truly understand the world the way a child does, perceiving it not as a collection of abstract features to be processed, but as a meaningful environment full of objects and possibilities and social significance. This reversal of expectations has become so normalized within the fields of artificial intelligence and cognitive science that researchers now treat it as an expected feature of machine learning rather than a surprising anomaly. The early pioneers in artificial intelligence made assumptions about what would be difficult and what would be easy that have been repeatedly confounded by subsequent developments. They believed that if they could teach a machine to play chess or prove mathematical theorems, they would have captured something essential about human intelligence, and that from there, all other capabilities would follow naturally. Imagine a scenario where a time traveler journeys into the past and prevents their own birth by killing their grandparent before that grandparent ever met their grandchild's other grandparent, which would mean the time traveler was never born, which means they could never have traveled back in time to kill their grandparent in the first place, and yet the act remains somehow committed despite its logical impossibility. This is the ontological paradox, a conceptual knot that sits at the intersection of causality, existence, and the nature of events themselves. The ontological paradox asks a deceptively simple question: how can something exist or occur when the very conditions necessary for its existence or occurrence are negated by the consequences of that existence or occurrence? It is not merely a puzzle of time and causality, though those elements are certainly present, but rather a fundamental challenge to our understanding of what it means for something to be real, to happen, or to have ever mattered at all. The classic illustration of this paradox emerges most clearly when we consider the grandfather paradox and its variations, where a time traveler returns to an earlier moment and performs an action that would logically prevent their own existence. The traveler steps into a time machine, travels backward through decades or centuries, locates their grandfather, and commits an act that prevents that ancestor from reproducing or surviving long enough to have children. The logical consequence is immediate and inescapable. If the grandfather never has children, then the grandchild who traveled backward through time could never have been born and therefore could never have entered the time machine in the first place. The action that was taken would be undone not by external forces, but by the internal contradiction of its own existence. And yet, in the moment of its commission, the act remains real. The gun fires, the accident occurs, the poison is administered. How does something that cannot logically exist manage to occur anyway? The psychological mechanism driving this paradox operates at a fundamental level of how we process causality and existence. Our brains have evolved to understand the world through chains of cause and effect, where one event leads inevitably to another, creating a tapestry of interconnected moments that flow from past to future with reasonable predictability. We expect that causes precede effects, that if something did not happen, its consequences also do not happen, and that reality maintains a basic internal consistency where contradictions cannot both be true simultaneously. The ontological paradox violates these intuitions so thoroughly that our minds struggle to even conceptualize what it would mean for such a contradiction to be genuinely real rather than merely hypothetical. Yet the paradox itself emerges not from some exotic physical scenario, but from the simple act of imagining what would happen if time could be traversed in both directions, a thought experiment that our minds can engage with intellectually even as we find it impossible to truly comprehend. What makes the ontological paradox particularly unsettling is that it challenges not just our understanding of cause and effect, but our understanding of existence itself. When we say something exists, we typically mean that it has properties, that it occurred in time, that it had effects on other things, that in some meaningful sense it is part of the fabric of reality. But the ontological paradox presents us with an action that must simultaneously exist and not exist, that must have happened and yet must be impossible to have happened. The very concept of existence begins to fray at the edges when confronted with this kind of logical contradiction. Some philosophers have suggested that such paradoxes simply cannot occur because the universe itself contains no logical contradictions, that the laws of physics would prevent any time traveler from ever acquiring the ability to commit such an act in the first place, or that reality would branch into multiple timelines to prevent the paradox from ever fully crystallizing. Others have argued that the paradox reveals something profound about the nature of time itself, suggesting that time might not be the linear progression we intuitively experience, but rather something more malleable, less constrained by the simple causality we assume. What is remarkable about this paradox is how it persists in our thinking and imagination despite having no clear resolution and no obvious real-world application, since we currently have no evidence that time travel backward is even physically possible. Yet we continue to puzzle over it, to write stories about it, to use it as a conceptual tool for exploring the boundaries of logic and reality. In the mid-19th century, an English economist and logician named William Stanley Jevons observed something that would become one of the most counterintuitive and persistent puzzles in economic and environmental thinking, a phenomenon that continues to baffle policymakers and sustainability advocates even in our modern era of climate consciousness and resource scarcity. Jevons was studying the coal industry during the Industrial Revolution, and he noticed a pattern that seemed to defy conventional wisdom about efficiency and conservation. When James Watt invented an improved steam engine that consumed significantly less coal while producing the same amount of power, Jevons expected that total coal consumption would naturally decrease as industries and businesses used less fuel to accomplish their goals. Instead, something remarkable and deeply troubling happened. The opposite occurred. The increased efficiency of steam engines made coal-powered machinery cheaper to operate, which made coal-powered factories and industries far more profitable and economically competitive. This dramatic reduction in operating costs led to an explosion in industrial expansion. Factories that had previously been uneconomical to run suddenly became viable. Coal-powered transportation became affordable for goods and people who had never before had access to such services. The market flooded with new applications for steam power, and the overall consumption of coal actually increased significantly, even as the efficiency of each individual machine improved substantially. This counterintuitive phenomenon came to be known as the Jevons Paradox, and it reveals something fundamental about human economics and consumption patterns that we still struggle to understand and address today. The mechanism behind this paradox operates through several interconnected psychological and economic principles that shape human behavior in subtle but powerful ways. When efficiency improvements reduce the cost of using a resource, that resource becomes more economically accessible and attractive to a broader range of consumers and industries, which fundamentally changes the demand curve in ways that economists had not fully appreciated. A farmer who previously could not afford to power multiple machines with steam engines suddenly finds it economically rational to purchase additional equipment and expand operations. Manufacturers discover new products and services that were economically unviable before efficiency improvements made them affordable. Consumers who previously could not justify the cost of certain goods and services suddenly find them within reach. This is not merely an abstract economic principle, but rather reflects a basic aspect of human nature and decision-making. When we save money through efficiency, we tend not to simply pocket those savings and reduce our consumption. Instead, we redirect those resources toward other purchases, services, and experiences that we had previously considered out of reach or insufficiently valuable to justify the expense. The psychological satisfaction of acquiring new goods and services generally outweighs the satisfaction of simply having less need for existing resources. Furthermore, in competitive markets, businesses that fail to expand and innovate when efficiency improvements make it possible find themselves at a disadvantage relative to competitors who do pursue aggressive expansion strategies. This creates a systemic pressure toward increased consumption that individual actors often cannot resist without sacrificing their economic viability. The Jevons Paradox has only become more relevant and more deeply entrenched in modern economics and environmental policy, even as awareness of the phenomenon has spread among academics and policy experts who recognize its implications for sustainability and resource management. We see this paradox playing out repeatedly in contemporary contexts where efficiency improvements have been introduced with the explicit intention of reducing resource consumption. More fuel-efficient automobiles have become cheaper to operate per mile, yet total vehicle miles driven has increased substantially rather than decreased, because lower per-mile costs make driving more economically attractive for additional purposes. More efficient heating systems have reduced the cost of maintaining warm buildings, yet this has encouraged people to heat larger spaces and maintain higher indoor temperatures than they might have otherwise, resulting in stable or even increased energy consumption despite technological improvements. More efficient agricultural practices have reduced the cost of food production, yet this has enabled the expansion of industrial agriculture and the development of food systems that require more total resources to produce and transport food globally. Imagine a city planner looking at a congested road network where thousands of commuters travel daily between the same 2 points, each person trying to minimize their own travel time by choosing what seems to be the fastest route available to them. The planner, hoping to improve overall traffic flow and reduce congestion, decides to add a new road to the network, a shortcut that connects two previously distant areas and provides drivers with what appears to be a clearly superior alternative. Common sense would suggest that adding infrastructure, adding options, and providing drivers with more choices should inevitably make things better for everyone. More roads mean more capacity, more alternatives mean shorter commutes, and additional routes should distribute traffic more evenly across the network. Yet something unexpected happens after the new road opens. Traffic congestion actually increases rather than decreases. Commute times grow longer for nearly everyone who travels on this network, and the overall efficiency of the entire system deteriorates despite the objective improvement in infrastructure. This counterintuitive phenomenon is Braess's paradox, named after the German mathematician Dietrich Braess, who discovered it in 1968. The mechanism underlying this paradox reveals something profound about systems where individual decision-making aggregates into collective outcomes. When drivers make choices based solely on minimizing their own travel time without consideration for how their choices affect others, they create what economists call a selfish routing problem. Each driver independently selects the route that appears fastest from their perspective at that particular moment, but because thousands of other drivers are making identical decisions based on identical information, everyone eventually converges on the same routes. Before the new road existed, drivers distributed themselves across available routes in a pattern that, while perhaps not optimal from a theoretical standpoint, had reached an equilibrium where no individual driver could improve their situation by unilaterally switching to a different route. This equilibrium, known as a Nash equilibrium, represents a stable state where everyone's choice is rational given what everyone else is doing. When the new road is added, it initially appears to offer a dramatic advantage, and naturally, drivers begin using it, believing they are improving their own situations. However, as more and more drivers flock to this new route, they create congestion on roads they previously avoided, and they also trigger a cascade of route switching among other drivers who now find their old routes becoming slower. The network eventually settles into a new equilibrium, but this new equilibrium is worse for nearly everyone because the new road essentially creates a temptation that leads each individual driver to make a choice that, when aggregated across the entire population, produces a collectively worse outcome than the original situation. The psychological and logical mechanism at work here involves a fundamental disconnect between individual rationality and collective welfare, a principle that appears throughout complex systems where multiple agents interact according to selfish optimization rules. Each driver's decision-making process is entirely rational from their individual perspective. They are genuinely trying to minimize their own travel time, yet the aggregation of all these rational individual decisions produces an irrational collective result. This occurs because drivers lack perfect information about how their choice will affect the network, and they also lack coordination mechanisms that would allow them to collectively agree to avoid using the new road if doing so would benefit everyone. The new road acts as a trap because it seems beneficial but actually degrades system performance, demonstrating how adding resources to a system can sometimes make that system worse rather than better when the system relies on decentralized decision-making by self-interested actors. This paradox has been observed not only in traffic networks, but also in communication networks, electrical power grids, and various other complex systems where individual users compete for shared resources and make decisions based on their own perceived benefits without accounting for negative externalities imposed on others. The persistence of Braess's paradox in real-world systems reflects our deeply ingrained belief in the universal benefits of expansion and increased options, a belief so fundamental to modern thinking that we often fail to question whether more infrastructure genuinely produces better outcomes, or whether sometimes the addition of new choices and new resources can trigger cascading changes that ultimately diminish system performance for everyone involved. Imagine a judge in a courtroom who announces to a condemned prisoner that they will be hanged sometime during the following week, but the execution will be a surprise. The prisoner will not know which day it will occur until the morning of their death. The judge adds that the prisoner must not know in advance which day they will be hanged, meaning the hanging cannot occur on a day that the prisoner has already logically deduced it must occur. This creates a peculiar logical knot that has puzzled philosophers, mathematicians, and logicians for generations, and it remains one of the most fascinating paradoxes of self-referential reasoning and our ability to know what we think we can know. The paradox begins to unfold when we follow the prisoner's line of reasoning, which at first appears to be entirely sound and logical. The prisoner reasons that the hanging cannot possibly occur on Friday, because if it has not yet happened by Thursday evening, then the prisoner would know with absolute certainty that Friday must be the day of execution, and this would violate the judge's condition that the hanging be a surprise. Therefore, Friday is eliminated as a possibility. However, the prisoner continues this line of thinking backwards through the week. If Friday is impossible, then the hanging cannot occur on Thursday either, because if the prisoner survives until Thursday morning and knows that Friday is impossible, then they would logically deduce that Thursday must be the execution day, again violating the surprise condition. Following this same reasoning, the prisoner systematically eliminates Wednesday, then Tuesday, then Monday, and finally Sunday, concluding that the hanging cannot occur at all during the week. The prisoner feels relief, believing they have proven the judge's statement to be impossible, a logical contradiction that means they cannot be hanged as promised. Yet despite this seemingly airtight logical reasoning, the prisoner is hanged on, say, Wednesday morning, and the prisoner is genuinely surprised, having eliminated Wednesday through deductive logic. This is where the paradox truly reveals its depth and power. The prisoner's reasoning was flawless from a purely logical standpoint, yet it led to a false conclusion. The hanging occurs and is indeed unexpected, proving that the judge's original statement was not a logical contradiction, but rather a profound exploration of the limits of self-reference and recursive reasoning. What makes this paradox so intellectually troubling is that it appears to demonstrate a logical proof that something is impossible, yet that very thing occurs anyway. The mechanism that creates this paradox lies in a subtle but crucial distinction between different levels of knowledge and reasoning. The prisoner's logic commits what might be called a self-defeating application of reasoning. When the prisoner reasons backward from Friday, they assume that the judge's statement must be meaningful and true, but then they use that assumed truth to prove the statement is false or impossible. The prisoner is essentially trying to use logical deduction to escape a situation that is defined precisely by the prisoner's inability to use logical deduction to know when it will happen. The paradox emerges from the interaction between the judge's statement and the prisoner's knowledge of that statement. The judge is betting on the fact that once the prisoner has gone through the logical elimination process and concluded that the hanging is impossible, the prisoner will let down their guard. The prisoner becomes confident in their logical reasoning, and this confidence, paradoxically, becomes the very condition that allows the surprise to actually occur. When Wednesday arrives and the prisoner has survived until then, still believing that the hanging is impossible because they have logically eliminated all days, the execution can still be a genuine surprise to them, even though the judge's original statement has been perfectly fulfilled. This paradox highlights something profound about the nature of self-referential statements and the limitations of certain kinds of reasoning. It demonstrates that deductive logic, while powerful, can sometimes fail us when applied to situations that are inherently self-referential or that involve our own knowledge of what we are trying to deduce. The paradox also reveals how our confidence in logical reasoning can become a blind spot, causing us to overlook possibilities that are actually quite real. Despite decades of philosophical analysis and attempted resolutions, the unexpected hanging paradox persists as a genuine puzzle that challenges our intuitions about logic, knowledge, and the nature of surprise itself. Imagine you are sitting in a vast library filled with thousands of datasets from the natural world, and you begin to notice something extraordinarily peculiar. The numbers in these datasets do not behave the way probability would suggest they should. If you were to open a random book of financial records, or a collection of measurements from geological surveys, or a compilation of population statistics across different cities and nations, you would expect the first digit of these numbers to be distributed equally, with the digit 1 appearing roughly 1 time out of 9, just as 2 would appear 1 time out of 9, and so forth through 9. However, when you actually examine these real-world collections, something unexpected emerges. The digit 1 appears at the beginning of numbers far more frequently than it should, accounting for roughly 30% of all first digits, while the digit 9 appears in less than 5% of cases. This phenomenon, which was first formally described by physicist Frank Benford in 1938, though discovered earlier by mathematician Simon Newcomb, has come to be known as Benford's law, and it appears with remarkable consistency across numerous categories of naturally occurring data. The pattern follows a precise logarithmic distribution, where the probability of a number beginning with digit n is calculated as the logarithm of 1 plus 1 divided by n, creating a curve that tilts heavily toward the lower digits and drops off sharply toward 9. When you apply this law to datasets ranging from the lengths of rivers to the populations of cities, from stock market prices to the distribution of atoms in radioactive decay, from the Fibonacci sequence to electrical bills, the pattern emerges again and again with an almost unsettling regularity, as though the universe itself were written in a language that unconsciously favors smaller numbers. The mechanism underlying this strange behavior exists in the fundamental mathematics of how numbers scale across different magnitudes and units. When you consider numbers that span multiple orders of magnitude, ranging from the very small to the very large, the logarithmic nature of human perception and mathematical growth creates a natural bias toward lower first digits. Consider a dataset that begins with values around 100 and grows to 10,000. Any number between 100 and 199 will have 1 as its first digit, covering a range of 90 numbers, whereas numbers between 900 and 999 will also have 9 as their first digit, but this represents the same range numerically. However, in logarithmic space, the distance from 100 to 200 is far smaller than the distance from 900 to 9,000, which explains why sequences of numbers that grow exponentially or follow natural scales will accumulate more first digits of 1. The Fibonacci sequence demonstrates this principle elegantly, as each number is generated by adding the previous 2, causing the sequence to grow exponentially. And when you examine the first digits of Fibonacci numbers, they follow Benford's law almost perfectly, despite there being no randomness whatsoever in the sequence. This same principle applies to any dataset that encompasses multiple scales of measurement or involves growth processes, whether compound interest in financial markets, population expansion in cities, or the physical dimensions of natural objects that have evolved and varied over time. What makes Benford's law truly paradoxical is that it persists and reveals itself in situations where we have absolutely no reason to expect it. Yet we have become so accustomed to its existence that we now use it as a tool for detecting fraud and anomalies rather than remaining perplexed by its presence. Forensic accountants and auditors now routinely apply Benford's law to financial records, understanding that fabricated data typically fails to follow the expected distribution because human intuition about randomness tends to distribute digits more evenly than natural processes do. Tax agencies around the world have incorporated Benford's law into their fraud detection systems, flagging datasets that deviate significantly from the expected logarithmic pattern, which has proven remarkably effective at identifying falsified records and suspicious financial activities. Election officials have used Benford's law to detect electoral fraud, though with considerably more debate about its reliability in that context. The very fact that we have normalized this once counterintuitive pattern into a practical detection tool speaks to how thoroughly we have integrated this mathematical anomaly into our understanding of the world, accepting it as a fundamental property of naturally occurring data without fully comprehending why the universe should care about logarithmic distributions when we write do. Imagine a mathematical shape so peculiar that it defies the intuition of every person who first encounters it. A three-dimensional form that possesses a finite volume, yet an infinite surface area, a contradiction so profound that mathematicians themselves struggled to accept its validity when it was first rigorously described in the 17th century by the Italian mathematician Evangelista Torricelli. This shape is known as Gabriel's horn, named after the archangel Gabriel, who is said to blow a trumpet at the end of times, and the horn's properties create one of the most bewildering paradoxes in mathematics that challenges our fundamental understanding of infinity, space, and the nature of physical reality itself. The horn is constructed by taking the curve defined by the equation y equals 1 divided by x, where x is greater than or equal to 1, and then rotating this hyperbolic curve around the horizontal x-axis to create a three-dimensional solid of revolution. When you perform this mathematical operation, you generate a shape that looks remarkably like an actual trumpet or horn, with a wide opening on one end that gradually tapers down to an infinitely thin point as it extends outward, asymptotically approaching but never quite reaching the axis of rotation. The paradox emerges when you apply the mathematical formulas for calculating volume and surface area to this shape, because when mathematicians compute the volume of Gabriel's horn using integration techniques, they discover that the volume is finite and equals exactly pi cubic units, a concrete number that you could theoretically pour liquid into and fill completely. However, when those same mathematicians calculate the surface area of this same horn using the identical mathematical methods and principles, they find that the surface area is infinite, suggesting that you would need an infinite amount of paint to cover the outer surface of this object. Yet somehow this infinitely large surface area contains a finite volume. This creates the famous paradox that became known as Gabriel's horn. You could theoretically fill the horn with a finite amount of paint, yet you could never paint the outside of it because doing so would require an infinite quantity of paint, a logical impossibility that seems to violate every principle of common sense and physical intuition about how objects in space should behave. The psychological mechanism that makes this paradox so compelling and so disturbing to contemplate is rooted in our deep evolutionary intuition about scaling and proportion, because in all observable physical reality, objects that contain large volumes tend to have correspondingly large surface areas, and objects that are difficult to paint tend to contain proportionally large volumes as well. Our brains have been shaped by millions of years of interaction with a three-dimensional physical world where these intuitions hold true, and Gabriel's horn represents a mathematical object that violates this fundamental expectation in a way that feels almost offensive to our sense of how reality should operate. The paradox persists not because it represents a logical error or a flaw in mathematical reasoning, but rather because it reveals a genuine feature of infinity that exists entirely outside the realm of physical instantiation. because while Gabriel's horn cannot exist as an actual physical object in the real world, it exists perfectly as a mathematical abstraction where the rules of infinity apply in ways that human intuition was never evolved to comprehend. Many people find themselves unable to fully accept this paradox despite its mathematical validity, because accepting it requires acknowledging that infinity behaves in ways that are fundamentally alien to our experience, that a shape can be simultaneously bounded in one measurable dimension yet unbounded in another, that the universe of pure mathematics contains genuine truths that have no correspondence to any physical reality we can ever directly observe or test. We have normalized Gabriel's horn by compartmentalizing it within the realm of abstract mathematics, treating it as an interesting intellectual curiosity rather than a genuine challenge to our understanding of how three-dimensional space actually functions. And this compartmentalization allows us to continue moving through the world without constantly confronting the unsettling implications of the paradox. The horn demonstrates that infinity is not a simple concept that scales predictably with our intuitions, but rather a realm where the normal rules of proportion and scaling break down entirely, where the vastness of a measurement in one dimension tells you nothing about the vastness of measurements in another dimension, and where seemingly fundamental relationships between properties dissolve into paradox. Imagine standing on a beach with a measuring tape, tasked with the simple objective of measuring the length of your country's coastline, a measurement that seems as though it should be straightforward and definitive, fixed like all other geographical features on a map. Yet as you begin this task, something peculiar emerges from the measurement itself, something that defies intuition and challenges our most basic assumptions about how the physical world can be quantified and understood. The Coastline Paradox reveals that the length of a coastline is not a fixed value at all, but rather a number that changes dramatically depending on the scale of measurement you choose to employ, growing longer and longer the more closely you examine it, a phenomenon that has puzzled mathematicians, geographers, and scientists for decades and continues to challenge our understanding of measurement, scale, and the nature of physical boundaries themselves. The mechanics of this paradox emerge from a deceptively simple principle that becomes increasingly complex the more you contemplate it. When you measure a coastline using a large measuring unit, say a ruler that is 1 kilometer long, you get a relatively modest total length because your measurement tool skips over all the small details, the tiny inlets and rocky protrusions and small bays that exist at smaller scales. But when you switch to a smaller measuring unit, perhaps a ruler that is 100 meters long, suddenly your measurement encompasses more of these previously invisible features, and your total length increases noticeably. As you continue to reduce the size of your measurement tool, examining the coastline at increasingly granular levels, the total measured length continues to grow, sometimes dramatically, because you are now capturing smaller and smaller irregularities, the miniature coves and pebbles and wave-worn rocks that were invisible at larger scales. This process theoretically continues infinitely. As you move from meters to centimeters to millimeters to the molecular level and beyond, each reduction in measurement scale revealing new complexity and adding length to your total, suggesting that a coastline might actually possess infinite length, a conclusion that seems absurd when we consider that we are measuring something that occupies a finite space on our planet. This peculiar behavior arises from the fractal nature of coastlines, a mathematical property that means coastlines exhibit similar patterns of complexity at multiple scales, containing endless detail no matter how closely you examine them. The coast does not smooth out as you zoom in closer, as many geographical features might, but instead reveals ever more complexity, more jaggedness, more intricate patterns, much like the famous Mandelbrot set or other fractal shapes that mathematicians have studied extensively. This self-similar quality means that a small section of coastline, when magnified, resembles the larger coastline from which it was taken, creating a recursive quality that continues indefinitely. Some coastlines, particularly those shaped by glaciation or rocky geology, are especially fractal in nature, exhibiting this property far more dramatically than others, which explains why some nations struggle far more than others when attempting to define and defend their coastal borders with precision. The implications of this paradox extend far beyond mere mathematical curiosity into the practical world of geography, international law, and political boundaries. Countries must define their coastline lengths for various official purposes, from calculating exclusive economic zones to establishing maritime boundaries with neighbors, and yet the Coastline Paradox means that no single answer exists without first establishing arbitrary conventions about measurement scale. Some nations have adopted specific measurement methodologies, defining their coastline length based on measurements taken at a particular scale using particular tools, creating official numbers that are more political decisions than physical facts. Yet despite the fundamental instability of coastline measurement, the world continues to operate as though coastlines have definite, unchanging lengths, treating what are essentially arbitrary conventions as though they were immutable geographical realities. We have normalized this paradox so completely that most people never question it, never consider that the coastline length they might learn in a geography class is not a discovered fact, but rather a consensus decision about how to measure something inherently unmeasurable. This paradox persists and remains largely unexamined in our collective consciousness because it does not affect daily life in any noticeable way, because the practical consequences of this mathematical quirk are usually absorbed by bureaucratic processes and international agreements that handle such ambiguities behind the scenes. Consider for a moment the strange and persistent feeling that your friends seem to have more friends than you do, a sensation that many people report experiencing with surprising regularity despite the mathematical impossibility of this being universally true. When you look around at your social circle, you might notice that the people you consider your closest companions appear to be more socially connected, more popular, or simply better at maintaining a wider network of relationships than you yourself are. And this observation might lead you to wonder whether you are somehow less skilled at friendship, or whether you occupy a peculiar position within the social landscape. This phenomenon, which researchers and sociologists have termed the friendship paradox, reveals something profound about how social networks actually function and how our perception of them becomes systematically skewed by the very structure of human connection itself. The paradox emerges from a deceptively simple mathematical truth. People tend to befriend others who have many friends, while people with few friends tend to befriend fewer people in return, which means that when you survey your own friend group, you are necessarily sampling a group that is, on average, more popular and more socially connected than a random selection of the population would be. In other words, your friends were not selected randomly from humanity. They were selected from the pool of people you encountered and chose to befriend, and this pool is inherently skewed toward people with higher social connectivity. When you examine the friend counts of your own friends, you are looking at a biased sample of the social network, one that overrepresents highly connected individuals, because it is precisely those individuals who are more likely to be your friends in the first place. The mechanism behind this phenomenon operates at multiple levels simultaneously, beginning with the simple observation that popular people, by definition, have more social connections, which means they are more likely to be encountered by any given individual and more likely to be selected as a friend when they are encountered. Furthermore, people with many friends create more opportunities for others to become their friends, simply by virtue of the fact that they interact with more people and attend more social gatherings, while people with few friends have fewer such opportunities to create. This creates a systematic bias in the sampling process that generates the paradox. Your friends are not representative of the broader population because they were drawn from a process that was more likely to select highly social individuals. The psychological experience of the friendship paradox is intensified by the fact that we tend to be aware of our friends' social activities through social media and other broadcasting mechanisms that make their social connections visible in ways that were simply impossible in earlier eras, allowing us to compare our own social engagement to theirs in a manner that feels immediate and quantifiable. When you scroll through social media and see that your friend has attended 5 social gatherings this month while you attended 1, or that they have accumulated 300 online connections while you have accumulated 50. The friendship paradox transforms from an abstract mathematical phenomenon into a concrete, emotionally resonant experience that can generate feelings of social inadequacy or isolation. This visibility amplification means that the paradox is no longer merely a mathematical curiosity, but has become integrated into the emotional landscape of modern social life, shaping how people perceive their own social status and competence. The persistence of the friendship paradox, despite widespread awareness of the mathematical principles underlying it, reveals something important about the nature of human perception and the resilience of intuitive, felt experiences in the face of logical understanding. Even knowing that the paradox is mathematically inevitable and that it is not a reflection of personal failure or social deficiency, people continue to experience the discomfort of believing their friends are more socially successful than they are, a phenomenon that suggests that intellectual comprehension of a logical principle does not automatically dissolve the emotional or experiential reality of that principle in action. The friendship paradox has become normalized to the point where it generates no particular surprise or investigation. Instead, it feels like a simple fact of social life that some people are naturally more connected and more popular than others, when in reality it reflects a quirk of how networks are structured and how we sample from them rather than any meaningful difference in social skill or worth. Imagine you are sitting in a room with 23 other people, which means there are 24 individuals total in that space, and someone poses a simple question to the group. What are the odds that at least 2 people in this room share the same birthday, meaning they were born on the same day of the year, though not necessarily in the same year? Most people, when confronted with this question, would instinctively calculate the probability by dividing 24 by 365, arriving at a rough estimate of around 6 or 7%, which seems extraordinarily unlikely. Yet the actual probability that at least 2 people share a birthday in a group of 24 is approximately 51%, meaning that in more cases than not, you will find a matching pair. This counterintuitive result is what mathematicians and statisticians refer to as the birthday paradox, and it stands as one of the most genuinely surprising mathematical phenomena that most people encounter in their lifetime, partly because it defies our everyday intuition so dramatically, and partly because the explanation, once understood, feels almost embarrassingly obvious in retrospect. The psychological mechanism that drives this paradox lies in the fundamental way human minds approach probability problems, specifically in how we tend to compare ourselves individually to the rest of the group rather than calculating all possible pairwise combinations. When someone asks about the birthday problem, your brain naturally thinks about the probability that someone else shares your specific birthday, which is indeed quite low, around 1 in 365. This anchoring to your own position creates a cognitive bias that prevents you from recognizing the actual mathematical structure of the problem. However, the true probability calculation does not compare each person to a fixed reference point, but instead considers every possible pair of people in the room, and the number of such pairs grows exponentially as the group size increases. With 24 people, there are exactly 276 possible pairs, which means there are 276 separate opportunities for a birthday match to occur. When you reframe the problem in this way, suddenly the 51% probability becomes far more plausible, because you are essentially asking whether any one of those 276 pairs happens to match, rather than whether one specific person matches your birthday. The mathematical beauty of this paradox is that it demonstrates the exponential growth of combinations in ways that our linear intuition completely fails to anticipate, and this same principle applies to countless real-world scenarios that we encounter without realizing their connection to this fundamental truth. As the group size increases from a handful of people toward 50 or 60 individuals, the probability of a match approaches near certainty, with 57 people in a room generating approximately 99% odds of a shared birthday. This explosive shift from improbable to almost inevitable happens in a relatively narrow range of group sizes, which further illustrates how poorly calibrated human intuition becomes when confronting combinatorial explosion. The paradox has been verified countless times in practical settings, in schools and offices and social gatherings, where statisticians have documented actual birthday matches in groups far smaller than most people would have predicted. Yet despite this repeated empirical validation, the finding continues to surprise people even after they have learned the explanation, because intuitive understanding does not always follow immediately after intellectual understanding. What makes the birthday paradox particularly fascinating is how it has become normalized within mathematics education and probability discourse, where it serves as a canonical example of counterintuitive thinking, yet in everyday life, most people remain entirely unaware of this principle, meaning that surprise and disbelief remain the standard response whenever someone encounters this result for the first time. The paradox persists in our collective consciousness not because there is any logical reason for it to be paradoxical, but simply because human brains are not naturally equipped to handle combinatorial reasoning at the scales required to make accurate predictions about such scenarios. We have evolved to navigate social groups of limited size through direct observation and pattern recognition, not through abstract calculation of exponential growth, and this evolutionary mismatch between our cognitive tools and the mathematical reality of the world continues to produce these moments of surprise and wonder when we finally confront the actual numbers. Imagine a hotel that exists not in the physical world, but in the realm of pure mathematics, a thought experiment conceived by the German mathematician David Hilbert in the early 20th century, designed to help us understand the deeply counterintuitive nature of infinity and how our everyday intuitions about space, capacity, and numbers break down when we venture into the infinite realm. This hotel, like any ordinary hotel, has rooms arranged sequentially, each one numbered with a whole number, room 1, room 2, room 3, continuing forever without end in a perfectly orderly fashion. The hotel appears at first glance to operate according to the normal rules we understand from the real world. Guests arrive, they are assigned rooms, and they sleep in those rooms for the night. But here is where the strangeness begins, where the paradox reveals itself, because this hotel has one extraordinary and seemingly impossible property. It has infinitely many rooms, and despite this, it is always completely full. Every single room is occupied by a guest, and yet, when a new guest arrives seeking shelter, the manager never turns them away, never says the hotel is at capacity, but instead welcomes them and finds them a place to sleep. And this happens again and again, infinitely many times. When the first new guest arrives at the already full hotel, the manager does something that would be impossible in any real hotel. He asks every guest to move one room over. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, the guest in room 3 moves to room 4, and so on, moving infinitely far down the corridor. Each guest vacates their current room and occupies the next one, and in doing so, room 1 becomes empty, ready for the new arrival. But then comes an even stranger scenario. What if infinitely many guests arrive all at once, perhaps a bus filled with countably infinite passengers? The manager does not hesitate, does not panic at the apparent impossibility of the situation. Instead, he asks every current guest to move from their room number n to room number 2 times n, so the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so forth. All the current guests occupy the even-numbered rooms, which despite being infinite in quantity, are still only half of the infinite rooms in the hotel, leaving all the odd-numbered rooms vacant and ready for the infinitely many new arrivals to settle into room 1, room 3, room 5, continuing infinitely onward. The paradox deepens further when we consider scenarios involving different types of infinity, when infinitely many buses each containing infinitely many passengers arrive simultaneously, yet the manager still manages to accommodate everyone through increasingly complex mathematical arrangements, assigning guests using diagonal enumeration methods that ensure every guest, no matter how many arrive, receives a room. The psychological mechanism underlying our discomfort with Hilbert's hotel stems from our evolutionary heritage as creatures who live in a fundamentally finite world where resources are limited, where occupancy really does mean full, and where adding more guests to a full space requires removing existing guests. Our brains evolved to manage scarcity, to count up to reasonable numbers, to understand that a hotel with 1,000 rooms can accommodate 1,000 guests but not 1,001, and this intuition served us well for millions of years. We developed an internalized logic that capacity means something real and immutable, that infinity is simply a very large number rather than a fundamentally different kind of quantity altogether. Hilbert's hotel shatters this intuition because it reveals that infinity does not behave like large numbers. Infinity possesses properties that seem to violate the basic rules we assume govern all reality. We find the scenario deeply disturbing not because it is logically flawed, but because it exposes the inadequacy of our intuitive understanding of quantity and space. The manager's ability to always find room for new guests, no matter how many arrive, seems to contradict the very definition of being full. Yet mathematically it is perfectly sound, perfectly consistent, perfectly demonstrable once we accept the axioms of infinite mathematics. We have normalized this paradox in the century since Hilbert proposed it, integrating it into mathematical education as an accepted fact rather than a persistent impossibility. Yet the unease remains, that lingering sense that something has been violated, that we have been shown a logical sleight of hand that technically works, but somehow feels like cheating against the rules of reality itself, and this normalization itself is remarkable. How we have collectively agreed to accept that infinity operates by different rules than we expect, that are. Imagine a philosophical thought experiment that has perplexed mathematicians, philosophers, and probability theorists for decades, one that forces us to confront the nature of consciousness, probability, and personal identity in ways that seem almost impossible to resolve. This is the Sleeping Beauty problem, a puzzle so deceptively simple in its setup, yet so profoundly complex in its implications that it has generated thousands of academic papers and created two seemingly irreconcilable camps of thinkers who cannot agree on the correct answer. The scenario begins on a Sunday evening when a woman known as Sleeping Beauty voluntarily enters into an experiment with researchers who explain the protocol in advance. On Sunday night, she is put to sleep through a process of induced unconsciousness, and while she sleeps, a fair coin is flipped once to determine the course of the experiment. If the coin lands on heads, she will be awakened on Monday, interviewed about her beliefs, and then put back to sleep with her memory of the interview erased before the experiment concludes on Tuesday. If the coin lands on tails, however, the scenario becomes far more complex. She will still be awakened on Monday, interviewed, and returned to sleep with her memory erased, but then on Tuesday she will be awakened again, interviewed a second time, and the experiment will finally conclude. The crucial detail that makes this problem so vexing is that Sleeping Beauty knows all of this in advance, but cannot remember any of her previous awakenings once they occur because her memory is chemically erased each time she is put back to sleep. Now the central question emerges with deceptive simplicity. When Sleeping Beauty wakes up during the experiment, what should her credence be, meaning her subjective probability assessment that the coin landed on heads? This is where the paradox reveals itself in full force, because there are two seemingly rational approaches that lead to contradictory answers, and both positions have compelling arguments behind them. The first position, held by those who call themselves halfers, argues that Sleeping Beauty should assign a probability of 1/2 to the coin having landed on heads. Their reasoning proceeds from the fact that the coin was fair when it was flipped, and nothing about Sleeping Beauty's awakening should rationally cause her to update her belief about a coin flip that was completed before she lost consciousness. From her subjective perspective upon waking, she has no new evidence that could possibly distinguish between a heads outcome and a tails outcome because in both scenarios she experiences being awakened and interviewed. The coin was fair, it is still fair in her reasoning, and therefore it should remain at 50% probability, they argue, seemingly with perfect logic and rationality on their side. However, there exists a second camp of equally intelligent thinkers who call themselves thirders, and they reach a radically different conclusion using reasoning that seems just as logically sound. The thirders argue that Sleeping Beauty should assign a probability of only 1/3 to the coin having landed on heads. Their argument rests on a careful analysis of how many times Sleeping Beauty will find herself in the situation of being awakened and conscious during the experiment. If the coin landed on heads, she will be awakened exactly once. If the coin landed on tails, she will be awakened exactly twice. Since she has no way of knowing which awakening she is currently experiencing, and since she should weight her probabilities by the number of possible awakenings, she must reason as follows. There are 3 equally likely possible awakenings that could occur across the entire experiment, 1 from the heads scenario and 2 from the tails scenario. Since she is currently in one of these 3 possible awakenings, and only one of the 3 is associated with heads, the probability of heads must be 1/3. This too seems perfectly rational when considered carefully, yet it directly contradicts the halfer's conclusion. The mechanism that generates this paradox lies in the fundamental question of how to apply probability theory to situations where the same person experiences multiple instances of consciousness without memory continuity. When we talk about probability in ordinary circumstances, we assume that the observer maintains continuous consciousness and memory, allowing us to count events and outcomes in straightforward ways. But the Sleeping Beauty problem introduces a scenario where consciousness is disrupted and reset, creating an ambiguity about how to count the observer's instantiations or awakenings. Imagine a situation where a treatment appears to be more effective than an alternative treatment when you look at the overall data, yet somehow becomes less effective when you break that same data down into smaller, more detailed groups. This is Simpson's paradox, a statistical phenomenon that reveals how aggregated data can tell a completely different story than disaggregated data, creating a situation where a trend reverses itself entirely when you examine the underlying subgroups. The paradox demonstrates that the conclusions we draw from data are not always as straightforward as they initially appear, and that our intuitions about correlation and causation can be thoroughly misleading when we fail to account for what statisticians call confounding variables. In the real world, this paradox has manifested in cases ranging from medical treatments and university admissions to employment discrimination and sports statistics, making it one of the most practically relevant yet psychologically counterintuitive phenomena in data analysis. For instance, imagine two hospitals, Hospital A and Hospital B, and they are being evaluated based on the survival rates of their surgical patients. When you look at the overall data across all types of surgeries, Hospital A appears to have a higher survival rate than Hospital B, perhaps 85% compared to 80%. This seems to suggest that Hospital A is the better hospital and that patients should preferentially seek treatment there. However, when researchers break down the data by type of surgery, something startling emerges. For simple, low-risk surgeries like appendectomies, Hospital B actually has a higher survival rate than Hospital A. For complex, high-risk surgeries like open-heart procedures, Hospital B again has a higher survival rate than Hospital A, so Hospital B is better at both simple and complex surgeries, yet Hospital A still shows a higher overall survival rate. How is this possible? The answer lies in the composition of patients at each hospital. Hospital A, perhaps being a larger or more prestigious institution, attracts more patients with simple, low-risk conditions who are likely to survive regardless of the quality of care they receive. Hospital B specializes in complex cases and attracts sicker patients with more serious conditions, meaning their overall survival rate is dragged down by the inherently higher mortality rate of their patient population. When you aggregate the data without accounting for this difference in patient severity, Hospital A's superior outcome is merely a reflection of who comes through the door, not the quality of medicine being practiced. This phenomenon occurs because the composition of the subgroups differs in a way that directly relates to the outcome being measured, creating what is called a confounding variable. The confounding variable in the hospital example is patient severity or complexity of the condition being treated. Because this variable affects both which hospital patients choose and how likely they are to survive, it creates a reversal in the relationship when data is aggregated versus disaggregated. The human mind, when presented with raw statistics, tends to accept aggregate trends at face value without considering whether the composition of the groups might be systematically different in ways that explain the overall pattern. We are pattern-matching creatures who look for simple explanations, and a single number like 85% survival rate feels more concrete and trustworthy than the acknowledgement that this number emerges from a complex mixture of patient populations with different baseline risks. The paradox persists in real-world decision-making because it requires a level of statistical sophistication and skepticism that most people are not trained to apply consistently. When we read that one treatment has a higher success rate than another, or that one institution performs better than another, we naturally assume that this difference reflects some inherent quality difference between the treatments or institutions themselves. But Simpson's paradox whispers that this assumption might be dangerously wrong. It is a reminder that data is not objective truth by itself. Rather, it is a representation of reality filtered through the choices about how to collect and aggregate it. The paradox also reveals something psychologically important about how authority and expertise function in our society. Statistical analyses are often presented by institutions or experts as definitive answers, and because most people lack the statistical training to scrutinize the underlying methodology, they accept these conclusions. Yet a paradox can easily hide within the aggregation, reversing the entire meaning of the data without anyone noticing if the disaggregated information is not also examined. Imagine you are presented with two identical envelopes, and you are told that one contains twice as much money as the other, though you do not know which is which or what the actual amounts are. You are allowed to open one envelope and examine its contents before making your final decision. Let us say you open the first envelope and discover it contains $100. Now you face a choice. You can keep this $100 or you can switch to the other envelope, trusting that it might contain either $50 or $200. This is the two envelopes problem, and it presents a deeply counterintuitive paradox that has troubled mathematicians, philosophers, and logicians for decades, existing as a peculiar monument to the ways our reasoning can lead us astray when we apply probability and expectation to situations with hidden information. The logical mechanism that creates this puzzle operates through the calculation of expected value, When you examine the $100 in your first envelope, your mind naturally begins to reason about the other envelope. If the other envelope contains twice as much, it holds $200, and if it contains half as much, it holds $50. Assuming you believe these two outcomes are equally probable, you might calculate that the expected value of switching is simply zero point 0.5 multiplied by 50 plus zero point 0.5 multiplied by 200, which equals $125. This is greater than the $100 you currently hold, so the logic of expected value seems to suggest you should always switch to the other envelope. But here emerges the peculiar contradiction that defines this problem. If you had instead opened the second envelope first and found $100 inside, the exact same calculation would apply, and you would again conclude that switching offers a better expected value. In fact, this logic would suggest that no matter which envelope you open first, and no matter what amount you find inside, you should perpetually switch back and forth between the envelopes, always believing the other one is more valuable. This infinite regress of switching reveals that something has gone fundamentally wrong with the reasoning process, yet it is difficult to identify precisely where the error lies, which is what makes this paradox so persistent and troubling. The resolution to this puzzle, though it takes considerable effort to appreciate fully, involves recognizing that we cannot assign probabilities to unknown values in the way the paradox implicitly assumes. When you open the first envelope and observe $100, you gain information, but this information does not allow you to treat the contents of the other envelope as following a simple 50-50 split between half and double the observed amount. The prior probability distribution over the possible amounts in the envelopes is crucial and cannot be ignored, yet the problem statement provides no information about this distribution. If we imagine that the envelopes were filled with amounts drawn from some particular probability distribution, then the calculation of expected value depends entirely on what that distribution is, and there is no universally correct answer that applies to all distributions. Furthermore, there is a subtle error embedded in how we frame the problem. When you condition on observing a specific amount in the first envelope, the posterior probability that the other envelope contains double or half that amount is not necessarily 50-50. This posterior probability depends on the underlying distribution from which the amounts were originally drawn. For instance, if the envelope filling process tends to use smaller amounts, then observing $100 might actually make it more likely that this is the larger of the two envelopes, which would suggest keeping it rather than switching. The paradox dissolves once we acknowledge that probability calculations require explicit information about the prior distribution, and without such information, we cannot meaningfully apply the machinery of expected value. What makes this problem persist despite its logical resolution is that it captures something genuine about human reasoning and the seductive appeal of certain mathematical arguments. We are drawn to the elegance of the switching logic, and we struggle to articulate why it fails without descending into technical discussions about prior distributions and conditional probability. The problem remains genuinely instructive because it teaches us that mathematical reasoning, while powerful, requires careful attention to assumptions and prior information, and that the appearance of logical necessity can mask hidden dependencies on unstated premises. Imagine standing in a room and watching an archer draw back a bowstring, the wooden shaft of an arrow nocked and ready for release. The archer lets go, and the arrow flies through the air toward a distant target. We observe this as motion, as a clear and undeniable example of something moving from one place to another through space. Yet if we were to pause and examine this moment with the kind of rigorous philosophical scrutiny that ancient thinkers brought to questions of motion and change, we would encounter a puzzle so deceptively simple that it has troubled the minds of philosophers for more than 2,000 years. This is Olbers Paradox, attributed to the ancient Greek philosopher Zeno of Allais, and it presents us with a fundamental challenge to our intuitive understanding of motion itself. The paradox works like this. At any given instant in time, an arrow in flight occupies a space that is equal to its own length. In other words, at any single moment, the arrow is at rest in a specific location, taking up a specific volume of space. If the arrow is at rest at every instant during its flight, then how can we say that the arrow is moving at all? Motion would seem to require the arrow to occupy different positions at different times, yet if we examine any individual instant of time, the arrow is stationary within that instant. The paradox suggests that an object cannot be in motion at a specific point in time because motion requires a duration, a passage from one moment to another, not the singular snapshot of a frozen instant. Yet a journey through time is nothing but the accumulation of all these individual instants strung together. If motion does not exist within any single instant, how can it exist in the journey as a whole? This is the core of Olbers Paradox, and it cuts directly at our understanding of what motion fundamentally is. To understand why this paradox seems so troubling, we must examine the conceptual machinery that makes it work. The paradox relies on a particular way of dividing time and space into discrete, countable units. When we break time into individual moments and space into individual points, we create a framework where motion becomes logically impossible. Each moment is a snapshot, a frozen frame, and within any single frozen frame, nothing moves. The arrow does not traverse space within an instant because an instant has no duration, no span from which something can move. Yet we experience the passage of time as continuous, not as a discrete series of moments. We perceive motion as a fluid, ongoing process, not as a collection of still images. The paradox emerges from the collision between our intuitive sense of continuous time and a logical framework that treats time as composed of indivisible instants. This problem connects intimately with questions about the nature of time itself. Is time continuous, forming an unbroken line from past through present to future, or is it composed of discrete moments? Is space likewise continuous or granular? The ancient Greeks had not fully resolved these questions, and in many ways we have not resolved them completely even today. Modern physics has given us sophisticated mathematical tools to describe motion, calculus in particular, which allows us to analyze continuous change through the concept of limits and infinitesimals. We can now say that velocity at an instant is defined as the limit of the average velocity over increasingly small time intervals approaching that instant. This mathematical framework sidesteps the logical problem by defining instantaneous velocity not as actual motion within an instant, but as the rate of change at that point. Yet this solution, elegant though it is, somewhat evades the underlying metaphysical question about what motion actually is in the fundamental nature of reality. What makes Olbers Paradox persist in human thought despite our modern understanding is that it touches upon something deeply counterintuitive about the relationship between time, space, and change. We have grown accustomed to treating the paradox as merely a logical puzzle with a mathematical solution, but the paradox endures because it points to a genuine mystery about how continuous motion emerges from instants that contain no motion. We have normalized this mystery by adopting mathematics as our authority, by accepting that velocity at an instant is defined through limits rather than direct observation. Yet the fundamental strangeness remains. How does an object that is stationary at every moment of its journey appear to be moving when we observe the journey as a whole? We have learned to live with this paradox not by fully resolving it, but by developing frameworks that allow us to calculate and predict motion without needing to fully comprehend its essential nature. Consider for a moment the ancient Cretan philosopher named Epimenides, who lived around 2,600 years ago on the island of Crete, a figure whose name has become permanently attached to one of the most fascinating logical puzzles that humanity has ever encountered. A paradox so elegant in its simplicity, yet so devastating in its implications that mathematicians, philosophers, and logicians have spent centuries trying to resolve it. The paradox itself emerges from a single statement, deceptively straightforward in its construction, that Epimenides allegedly proclaimed to his fellow Cretans: "All Cretans are liars." Now pause here and consider what this statement truly means and what happens when you attempt to evaluate its truth value. If the statement is true, then Epimenides, being a Cretan himself, must be a liar, which means his statement is false. But if his statement is false, then not all Cretans are liars, which suggests his statement might be true after all, creating a circular chain of reasoning that spirals endlessly without ever reaching solid ground. This is the fundamental mechanism of the paradox, a self-referential loop where the truth value of a statement depends on its own truth value in a way that generates logical contradiction. The psychological impact of encountering this paradox lies in how it violates our intuitive understanding of how language and logic should function, because we naturally assume that any statement must be either true or false, that the law of excluded middle applies universally, and yet here we find a statement that seems to elude this binary classification entirely. The mechanics of this paradox become even more apparent when we examine it through the lens of self-reference and circularity. When Epimenides makes his pronouncement about all Cretans being liars, he includes himself within the category of Cretans being discussed, which means the statement reaches back to evaluate itself. This self-referential quality is the key ingredient that transforms what might otherwise be a simple factual claim about the honesty of an ancient Mediterranean population into something that destabilizes logical systems. If we try to treat the statement formally, assigning it a truth value of true or false, we immediately discover that neither assignment is consistent. The statement creates what logicians call a fixed-point problem, where no stable solution exists because the very act of assigning a truth value leads to a contradiction that forces us to assign the opposite value, which then leads back to the original contradiction. This recursive loop has no exit point, no moment where we can rest assured that we have correctly evaluated the statement's validity. What makes the Epimenides Paradox particularly resilient despite its logical inconsistency is that it reveals something fundamental about the nature of language itself, namely that natural language allows for self-reference in ways that formal logical systems cannot easily accommodate. We use language constantly in our daily lives to make statements about statements, to talk about talking, to think about thinking, and we do this without any apparent problem. Yet when we isolate and magnify these self-referential structures, as the Epimenides paradox does, we discover that they can generate seemingly paradoxical situations. The paradox persists in our philosophical consciousness not because we have failed to resolve it, but because it points toward genuine limitations in how we can formalize truth and meaning. Various attempted solutions have emerged over the centuries, ranging from the suggestion that the statement is neither true nor false, but simply meaningless, to more sophisticated approaches using multi-valued logic systems that allow for truth values beyond the binary true and false, to sophisticated formal systems that carefully restrict the kinds of self-reference that are permitted within them. Yet despite these various proposed resolutions, the Epimenides paradox continues to fascinate and perplex because it seems to reveal that the very foundation of logical thought, the assumption that every meaningful statement must have a definite truth value, may itself be incomplete or require more nuanced understanding. We have normalized this paradox into our educational systems and philosophical traditions not by solving it definitively, but by accepting it as a fundamental lesson about the limits of formal logic and the special properties of self-referential statements. The paradox reminds us that language and logic, for all their power and precision, operate within boundaries that are not always immediately apparent, and that when we push language toward extremes of self-reference and circularity, we discover regions where our normal tools and assumptions simply do not apply cleanly or without contradiction. Consider the peculiar nature of words themselves, those linguistic units we use to describe the world around us, and then consider applying those same words to describe themselves in a strange act of linguistic self-reference that creates a most unsettling logical puzzle. The Grelling-Nelson Paradox, first formulated by Kurt Grelling and Leonard Nelson in 1908, presents us with a seemingly simple question that leads us directly into a logical abyss from which there appears to be no escape. We must begin by understanding the distinction between ontological and heterological words, which are terms that describe whether a word possesses the very property that it names. An ontological word is one that describes itself accurately, such as the word short, which is indeed a short word, or the word English, which is itself an English word, or the word polysyllabic, which contains multiple syllables and thus possesses the quality it describes. By contrast, a heterological word is one that does not possess the property it names, such as the word long, which is ironically a short word and therefore does not itself possess the quality of length that it describes, or the word monosyllabic, which contains 5 syllables and therefore fails to exemplify the very concept it represents. This distinction seems logical and perfectly reasonable at first consideration, allowing us to sort every descriptive word in our language into one of these two categories without any apparent difficulty or contradiction. However, the paradox emerges when we attempt to classify the word heterological itself by applying this very framework to it. We must ask ourselves whether heterological is an ontological word or a heterological word, which is to say, does the word heterological possess the quality of being heterological? If we answer that yes, heterological is itself heterological, meaning that it does not possess the property it names, then we have created a direct contradiction, because if it does not possess the property of being heterological, then it must be ontological by definition. Conversely, if we answer that no, heterological is not heterological but rather ontological, then we are claiming that it does possess the property it names, which means it must be heterological after all, because to be ontological is to possess the property one names, and the property named by heterological is precisely the property of not possessing the property one names. Thus we find ourselves caught in an endless logical loop, a vicious circle from which neither answer provides escape, and neither selection leads to consistency. The psychological mechanism at work within this paradox involves our natural tendency to treat language as though it exists outside the realm of the objects it describes, as though words are transparent tools that we use to discuss the world without themselves being part of the world they describe. We are accustomed to drawing a sharp distinction between the map and the territory, between the symbol and the thing symbolized, between the word and the referent, and this distinction has served us remarkably well throughout the history of human language and thought. Yet when we turn this same analytical machinery inward, when we attempt to use language to describe language itself, when words become both the tools of description and the objects being described simultaneously, our normal logical frameworks begin to fracture beneath the weight of this self-reference. The human mind struggles with self-referential problems because our cognitive architecture evolved to navigate a world of external objects and physical phenomena, not to contemplate the nature of our own thinking processes or the structure of our own linguistic systems at the level of abstract logic. The Grelling-Nelson Paradox forces us to confront the possibility that not all questions have answers, that language itself might contain inherent logical inconsistencies that cannot be resolved through careful thinking or more precise definitions, and that self-reference in language can produce genuinely paradoxical situations that resist resolution. What makes this paradox particularly troubling is that it does not require any advanced mathematics or specialized technical knowledge to understand, yet it cannot be dismissed as a mere trick of words or a product of linguistic confusion. The paradox persists because the distinction between ontological and heterological words is genuinely meaningful and useful in most contexts. Yet the moment we apply this distinction to the very word that names the second category, the logical system collapses into contradiction. Imagine you are sitting in your living room on a Wednesday evening, and you decide to purchase a lottery ticket for a drawing that will take place tomorrow night. The odds are catastrophically bad, perhaps 1 in 300 million, which means your individual chance of winning is so infinitesimally small that it rounds down to essentially zero in any practical mathematical sense. Yet despite knowing these odds with absolute certainty, despite understanding them intellectually, and even discussing them casually with friends, you find yourself genuinely hoping that your ticket will be the winning one. You check the numbers obsessively after the drawing. You experience a real flutter of anticipation in the moments before the results are announced. This psychological phenomenon sits at the heart of what philosophers call the lottery paradox, and it reveals something genuinely troubling about the nature of rational belief and human cognition that has puzzled thinkers for generations. The classical formulation of the lottery paradox was developed by philosopher John Kaczynski in the 1970s, and it proceeds from a deceptively simple logical structure that creates an almost impossible contradiction when examined closely. The paradox asks us to consider the following situation. You hold a ticket in a fair lottery with 1 million participants, and you know with absolute certainty that exactly one ticket will win and 999,999 will lose. Given these facts, it seems entirely rational for you to believe that your specific ticket will lose. The probability is 0.9999999%, which is so close to certainty that to refuse this belief seems almost absurdly irrational. You would be willing to bet significant money on your ticket losing, would you not? Most people would agree that this belief is justified and reasonable. However, here is where the paradox emerges with full force and creates a logical trap that has no satisfying resolution. If it is rational for you to believe that your ticket will lose, then by exactly the same reasoning, it should be rational for every other ticket holder to believe that their ticket will lose as well. There is nothing special about your ticket compared to any other ticket in the lottery. They are all equivalent from a probabilistic standpoint. Yet if everyone is rationally justified in believing that their ticket will lose, then everyone is rationally justified in believing that all 1 million tickets will lose. But this creates an obvious logical impossibility, because we know with absolute certainty that exactly one ticket must win. Therefore, we cannot all be correct in our beliefs, and this means that at least one person must be holding a rationally justified belief that happens to be false. This seems to violate our fundamental intuitions about what rationality and justification mean, because we typically assume that justified beliefs should correlate with truth, at least in the long run. The deeper mechanism underlying this paradox involves a tension between two different approaches to probability and rational belief that cannot be easily reconciled. The first approach, which we might call the classical or frequentist approach, focuses on the long-run behavior of repeatable events and the precise numerical odds. From this perspective, a belief is justified when it aligns with the actual probability, and a belief with odds of 0.99999% is clearly justified. The second approach, which philosophers call the closure principle or the principle of rational consistency, suggests that if you rationally believe multiple individual premises, then you must rationally believe any logical conclusion that follows from those premises. But as we have seen, applying this principle to the lottery leads directly to contradiction, because the individual rational beliefs do not combine into a rational collective belief. The persistence of the lottery paradox in philosophical discourse, despite centuries of analytical effort, reveals something profound about the limitations of our logical frameworks and the genuine incommensurability between how probability theory describes the world and how human rationality actually functions in practice. We have developed no universally accepted resolution because the paradox exposes a real fracture in our understanding, not merely a trick of language or a subtle logical error that clever analysis can eliminate. Various proposals have been made. Some philosophers suggest that we should reject the closure principle and accept that rational beliefs need not combine rationally, while others argue that we should adopt a different model of probabilistic reasoning altogether that does not rely on precise numerical odds. Imagine a fishery manager tasked with improving the health of a local ecosystem by introducing more nutrients into a previously nutrient-poor lake, a seemingly straightforward and beneficial intervention based on the assumption that more resources lead to better outcomes for the organisms living there. The manager introduces nitrogen and phosphorus, fertilizers that would logically seem to support the growth of aquatic plants and the fish that depend on them, yet something counterintuitive happens instead. The ecosystem destabilizes. Fish populations that were stable begin to crash unpredictably. What was meant to be an enrichment becomes an ecological catastrophe, and the manager is left puzzled, wondering how providing more of what seemed like a necessary resource could possibly harm the very system it was meant to support. This phenomenon is known as the paradox of enrichment, discovered through mathematical models in ecology, but repeatedly confirmed through field observations and laboratory experiments across countless ecosystems worldwide. The paradox reveals that in certain ecological systems, increasing the availability of resources does not lead to greater stability or improved conditions, but instead produces the opposite effect: increased instability, population volatility, and potential system collapse. The mechanism underlying this paradox operates through a cascade of interconnected biological processes that seem reasonable in isolation, but combine to create destabilizing feedback loops when resources become abundantly available. When nutrients are scarce in an ecosystem, predator and prey populations exist in a relatively stable balance because the scarcity itself acts as a natural brake on population growth. The prey population cannot explode because there simply are not enough resources to support rapid expansion, and consequently, the predator population remains controlled by the limited availability of prey. This creates what ecologists call a stable equilibrium, where populations fluctuate only slightly around a consistent average. However, when nutrient enrichment occurs, the prey species suddenly have access to far more food, and their population growth rate increases dramatically. The predators respond to this abundance of prey by increasing their own population, but here is where the destabilizing mechanism emerges. Because prey now reproduce so rapidly thanks to abundant nutrients, predators can also increase in numbers far more aggressively than before. This creates a scenario where the oscillations between predator and prey populations become increasingly extreme and unpredictable. The prey population explodes, then the predators follow with a delay, consuming the prey population so thoroughly that it crashes, then the predators starve in turn and their numbers plummet, allowing the prey to recover again. These swings grow wider and more violent with each cycle, eventually pushing one or both populations beyond recovery, particularly if the oscillations become severe enough that the predator population temporarily crashes to zero individuals. Additionally, nutrient enrichment often favors certain fast-growing algae species that can outcompete slower-growing aquatic plants, leading to algal blooms that shade out other organisms and create dead zones when the algae eventually die and decompose, consuming all available oxygen in the water. The abundance that seemed universally positive paradoxically creates conditions for instability and collapse. What makes this paradox particularly fascinating from a conceptual standpoint is how it persists as a blind spot in human resource management despite being well documented in scientific literature for decades. We have normalized and internalized the assumption that more resources always produce better outcomes, that scarcity is universally bad and abundance is universally good, when the reality is far more subtle and context-dependent. Conservation managers continue to struggle with the counterintuitive nature of the paradox because it violates our fundamental intuition about how systems should work. We have built entire economic and agricultural frameworks on the premise that resource enrichment leads to improvement, yet in complex ecological systems with predator-prey dynamics or competing species interactions, this assumption can be dangerously wrong. The paradox reminds us that stability and resilience sometimes depend on constraints rather than their removal, and that optimizing one variable in a complex system without understanding its full effects can produce outcomes opposite to our intentions. The persistence of this paradox in practical resource management reflects how difficult it is for human minds to grasp that abundance can generate fragility rather than robustness in certain configurations of living systems. Imagine sitting in a quiet room wearing headphones, listening to two musical notes play in sequence. The first note sounds higher in pitch, and the second note sounds lower, creating a descending pattern that your ear clearly perceives. Yet when the same sequence plays again, something peculiar happens. The notes seem to reverse their relationship, with what you heard as lower now seeming higher, even though the acoustic properties of the sounds remain absolutely identical. This is the Tritone Paradox, a fascinating auditory illusion discovered by psychologist Diana Deutsch in 1986 that reveals a fundamental breakdown in how our brains process musical pitch. The tritone paradox emerges from a specific construction of sound waves where two tones are separated by exactly 6 semitones, known as a tritone interval. Each note is actually composed of multiple octaves played simultaneously, creating an ambiguous stimulus that your auditory system cannot definitively resolve. When you hear the first sequence and perceive it as descending, your brain is making a choice about which octaves to prioritize, essentially choosing to focus on certain harmonic components while ignoring others. The remarkable aspect of this illusion is its profound subjectivity. Different listeners, and even the same listener in different contexts or on different days, perceive the direction of the musical movement completely differently. Some people consistently hear the sequence as ascending while others hear it as descending, and this perception appears to be influenced by factors including linguistic background, musical training, and possibly even the specific frequencies used in the presentation. When neuroscientists have studied the tritone paradox using brain imaging, they discovered that different regions of the auditory cortex activate depending on which direction an individual perceives the sequence moving, suggesting that the paradox represents a genuine ambiguity in how the brain processes this particular acoustic information rather than a simple failure of perception. The tritone paradox persists as a profound mystery because it demonstrates that pitch perception, which we typically think of as straightforward sensory information being transmitted from our ears to our brain, is actually a constructed experience built from incomplete and ambiguous data. Our brains do not passively receive pitch information like a recording device capturing sound. Instead, they actively interpret acoustic signals by making assumptions about what the sounds represent and how they should be organized. In the case of the tritone paradox, the acoustic stimulus is deliberately designed to be genuinely ambiguous, lacking clear information that would allow the brain to definitively determine whether the pitch is ascending or descending. The brain must therefore make an interpretive choice, and remarkably, different brains make different choices based on subtle differences in how they weight and prioritize different aspects of the acoustic signal. What makes the tritone paradox particularly unsettling is that it suggests the boundary between objective reality and subjective perception may be far more permeable than we typically assume. The sound waves themselves contain no information about direction because they are constructed to be symmetrical around the ambiguous point. Your perception is not revealing a hidden truth about the sounds. Your perception is literally creating the direction through the choices your brain makes during auditory processing. This means that when you listen to the Tritone Paradox and hear it moving in a particular direction, you are not discovering something that was already there. You are creating something that would not exist without your brain's interpretation. The persistence of the Tritone Paradox in the face of our understanding suggests that even after discovering these illusions and learning how they function, we cannot simply override our perceptual systems through conscious effort. You can know exactly how the Tritone Paradox works and still hear it moving in a direction that is different from how someone else hears it. You can even know that the stimulus is ambiguous and that your perception is constructed, and you still cannot control which interpretation your brain selects. This disconnect between knowledge and perception reveals something fundamental about the architecture of human consciousness. We are not unified observers rationally processing the world. We are collections of systems operating on different principles, some of which are involuntary and resistant to conscious control. The Tritone Paradox has become a subject of increasing interest to neuroscientists and cognitive psychologists precisely because it offers a window into these normally hidden processes through which our brains actively construct our experience of reality, and it demonstrates that what we perceive. Imagine you are presented with an urn containing colored balls, and you are told that the urn holds 100 balls total, but you are not given complete information about their distribution. You know for certain that 30 balls are red, but the remaining 70 balls are some combination of black and yellow balls in unknown proportions. Now imagine that you are offered a choice between two different bets, and the question becomes not about which bet is objectively better, but rather about what your intuition tells you to prefer, and whether that preference makes logical sense when examined carefully. In the first scenario, you can win a prize if you draw a red ball from the urn, or alternatively you can win the same prize if you draw a black ball from the urn. Most people find themselves attracted to the first bet, wagering on the red ball, because they know with certainty that 30 red balls exist in the urn. In the second scenario, you face a different choice where you can win the prize if you draw either a red or yellow ball, or you can win if you draw either a black or yellow ball. When faced with this second set of options, the same people who preferred red over black in the first scenario will typically prefer the option of black or yellow over red or yellow in the second scenario. This behavioral pattern was first documented by economist Daniel Ellsberg in 1961, and it reveals a profound inconsistency in how humans approach decision-making under conditions of uncertainty. The mechanism underlying this paradox emerges from something called ambiguity aversion, which is the human tendency to prefer situations where probabilities are known over situations where probabilities are unknown, even when the unknown situation might objectively offer equivalent or superior expected value. When you know that exactly 30 balls are red, you can calculate that you have a precisely 30% chance of drawing red on any single draw. But when you do not know the exact distribution of black and yellow balls among the remaining 70, your mind confronts genuine ambiguity, and this ambiguity creates a psychological discomfort that influences your choices in systematic ways. In the first scenario, choosing red feels safer because you understand the odds completely, whereas choosing black requires you to accept an unknown probability that could theoretically range anywhere from 0 to 70%. The preference for the known risk over the unknown risk seems intuitively reasonable at first glance, but the paradox reveals itself when you examine the second scenario more carefully. If you preferred red in the first case because you wanted to avoid ambiguity about black, you should logically prefer red or yellow in the second case, because that choice still maintains your preference for the known quantity of red balls. However, most people's intuition reverses in this second scenario, and they instead choose black or yellow, suggesting that their true motivation is not consistent ambiguity aversion, but rather something more subtle and contradictory in how they process probability and uncertainty. This paradox persists in human decision-making despite its logical inconsistency, because it reflects something fundamental about how our minds evolved to navigate an uncertain world. We are not naturally equipped to think in precise probabilistic terms, and when we face genuine ambiguity, our brains activate ancient threat detection systems that make us want to retreat toward what feels knowable and controllable. The existence of Ellsberg's paradox has led economists and psychologists to recognize that the classical expected utility theory, which assumes humans make perfectly rational choices by calculating expected values, fails to account for this very real and widespread phenomenon. Modern decision theory has been forced to incorporate concepts like ambiguity aversion and uncertainty aversion as fundamental aspects of human preference formation, acknowledging that our choices are not merely about outcomes, but about how confident we feel in our understanding of the situation. What makes this paradox particularly fascinating is that it has proven remarkably resistant to simple explanation or resolution, suggesting that the inconsistency reflects something deep about human cognition rather than a simple bias that can be easily corrected through education or awareness. Even when people understand the paradox logically and acknowledge the inconsistency in their own choices, they often find themselves unable or unwilling to change their preferences, implying that ambiguity aversion operates at a level of decision-making that exists somewhat beyond the reach of conscious rational deliberation. In the year 1953, a French economist named Maurice Allais presented a thought experiment that would challenge one of the most fundamental assumptions in economics and decision theory, an assumption that had been accepted as self-evident truth by virtually every rational actor and every mathematical model of human choice that had come before. The paradox he described was deceptively simple in its presentation, yet profoundly troubling in its implications, because it demonstrated that intelligent people consistently make choices that directly contradict their own stated preferences and the axioms of expected utility theory, which holds that rational decision-makers should always choose the option with the highest expected value. Consider first a scenario where you are presented with two lottery options, and you must choose between them without knowing which will ultimately be selected. In the first option, you receive $1 million with absolute certainty, with no risk whatsoever. In the second option, you have an 89% chance of winning $1 million, a 10% chance of winning $5 million, and a 1% chance of winning nothing at all. Most people, when faced with this choice, select the first option, the certain $1 million, because the guaranteed outcome feels safer and more reliable than the gamble, even though the mathematical expected value of the second option is actually higher. But now consider a second scenario with different probabilities. In the first option here, you have an 89% chance of winning $1 million and an 11% chance of winning nothing. In the second option, you have a 10% chance of winning $5 million and a 90% chance of winning nothing. When people are presented with this second scenario, the overwhelming majority switch their preference and choose the second option, the risky gamble with the higher potential payoff, even though the mathematical relationship between the two scenarios remains structurally identical when examined through the lens of expected utility theory. This reversal of preferences in response to mathematically equivalent scenarios reveals a fundamental inconsistency in how human beings actually evaluate risk and value, a reversal that cannot be accounted for by any rational decision-making model that depends solely on the expected monetary value of outcomes. The mechanism underlying this paradox operates through what psychologists call the certainty effect, a cognitive bias that causes people to overweight outcomes that are perceived as certain or nearly certain compared to outcomes that are uncertain or probabilistic. When the first scenario presents a 99% chance of winning something substantial, people focus intensely on that near certainty and feel compelled to secure it, treating the difference between 99% and 100% as catastrophic rather than marginal. But in the second scenario, when both options have relatively low probabilities of winning anything, that same certainty effect disappears because there is no near certain outcome to cling to, and suddenly the focus shifts to maximizing the potential payoff rather than minimizing the risk of total loss. This shift in reference point and focus is not irrational in any absolute sense, because it reflects how human psychology actually processes probability and value in the context of real decision-making. Yet it is decidedly irrational according to the mathematical models that economists had constructed to describe rational behavior. What makes the Allais paradox particularly persistent and resistant to resolution is that even after people understand the logical contradiction between their two choices, even after they comprehend that they have selected options that cannot both be true if they truly follow a consistent utility function, they often maintain their original preferences anyway. Because the psychological pull of certainty and the subjective experience of risk feels more real and immediate than the abstract principle of logical consistency. We have normalized this paradox by acknowledging that human decision-making deviates from perfect rationality, yet we continue to build economic models and financial systems that assume rationality as a baseline, creating an ever-widening gap between the mathematical theories we use to structure the world and the actual behavior of the human beings who must navigate that world. The paradox persists because it exposes the uncomfortable truth that our sense of risk, our emotional response to the possibility of loss, and our preference for certainty are not bugs in our decision-making apparatus, but rather fundamental features of human psychology that have evolved over millennia and that continue to guide our choices in ways that defy elegant mathematical formulation. Eugene Charles Catalan, a 19th-century mathematician, observed something peculiar about the very nature of infinity itself, a phenomenon that continues to perplex and fascinate mathematicians and philosophers to this day, precisely because it reveals something deeply counterintuitive about how we understand size, quantity, and the fundamental structure of mathematical reality. The paradox emerges when we consider two seemingly different infinities that, upon closer examination, turn out to be exactly the same size, which violates our intuitive understanding that some infinities ought to be larger than others based on how they are constructed. When we think about infinity in everyday terms, we imagine something without end, something boundless and immeasurable, yet mathematics has discovered that there are different types of infinity, different magnitudes of endlessness, and this discovery fundamentally challenges our ability to reason about the infinite using the tools we developed for finite quantities. Catalan's observation specifically concerns the relationship between the set of all natural numbers, 1, 2, 3, and so on forever, and the set of all rational numbers, which includes every fraction that can possibly be expressed as one integer divided by another integer, such as 1/2, 3/4, or 1,234 divided by 5,678. Our immediate intuition suggests that the rational numbers should be vastly larger in quantity than the natural numbers, because between any two natural numbers, there exist infinitely many rational numbers, and this observation seems to establish a clear hierarchy of size between these two infinities. If between 1 and 2 there are infinitely many fractions, and between 2 and 3 there are infinitely many more, and this pattern continues forever, then surely the total collection of all rational numbers must constitute a larger infinity than the natural numbers themselves, a more capacious infinity that contains the natural numbers as a tiny subset while extending infinitely further in multiple dimensions of mathematical space. However, through a brilliant and elegant mathematical argument known as Cantor's diagonal enumeration, mathematicians demonstrated that the set of all rational numbers can be arranged in a sequence, a list, one after another, in such a way that every single rational number appears exactly once somewhere in that infinite list, which means that the rational numbers, despite their apparent abundance and density, are countably infinite, exactly as infinite as the natural numbers themselves. No more and no less. This revelation creates the paradox that captivates our minds as we try to sleep, for it contradicts the very foundations of how we learn to think about quantities and sizes, how we developed our intuitive sense of comparison and magnitude throughout our entire lives and education. The mechanism underlying this counterintuitive result rests on a fundamental distinction between two concepts of size. The notion of density, which asks how thickly packed elements are within a given interval, and the notion of cardinality, which asks how many total elements exist in the entire set, regardless of how they are arranged or distributed throughout mathematical space. Between any two natural numbers lies an infinite density of rational numbers, yet the total count of rational numbers across all intervals combined is still only countably infinite, still capable of being arranged in a sequence where each rational number has a position, a place in the order, even though this seems to defy the logical structure of mathematical reality as our minds have constructed it through centuries of experience with finite quantities. We can list all rational numbers in a systematic way by arranging them according to the sum of their numerator and denominator, beginning with 1/1, then moving to 1/2 and 2/1, then 1/3, 2/2, and 3/1, and continuing this process indefinitely in a manner that guarantees every rational number will eventually appear somewhere on the list. However counterintuitive this systematic enumeration might seem when we consider the boundless abundance of fractions existing within even a single finite interval. The paradox persists in our minds not because it represents a logical impossibility or a genuine contradiction in mathematics, but because it reveals the limitations of human intuition when confronted with the infinite, exposing how our brains, evolved to navigate finite physical spaces and finite quantities, struggle to maintain consistent reasoning when projected into the realm of boundless magnitudes and endless collections. Consider the peculiar situation that unfolds within the domain of predictive modeling and statistical classification, where a system designed to make accurate decisions can achieve what appears to be exceptional performance metrics while simultaneously failing at its fundamental purpose in ways that are both counterintuitive and deeply troubling to those who encounter them. This is the accuracy paradox, a phenomenon that reveals a fundamental disconnect between how we measure success and what success actually means in practical application, exposing a gap so wide that our most celebrated models can be simultaneously brilliant and useless depending entirely on perspective and context. Imagine a scenario in which a medical diagnostic system is trained to identify a particular rare disease that affects only 1 in every 10,000 patients within a given population. And suppose that this system has achieved an accuracy rating of 99.99% on standardized tests, a figure that would ordinarily be considered extraordinary and worthy of celebration in virtually any domain of human endeavor. Yet when this system is deployed in the real world and asked to make actual diagnostic decisions for actual patients, something peculiar happens that undermines the apparent excellence of the measurement. The system simply predicts that everyone is healthy, that no one has the disease, that the negative case is always the correct case. And in doing so, it achieves that 99.99% accuracy score because the disease is indeed so rare that classifying everyone as disease-free produces a correct answer more than 99% of the time. The mechanism behind this paradox lies in the fundamental structure of how we calculate accuracy itself, which relies on a simple formula of correct predictions divided by total predictions, a metric that becomes dangerously misleading when the distribution of outcomes is severely imbalanced, when one category vastly outnumbers all others to such a dramatic degree that a model can achieve statistical excellence through mere indolence. Through the simple expedient of always choosing the most common option, regardless of whether that choice is actually justified by any genuine understanding or analysis. The paradox emerges because accuracy as a metric treats all correct predictions as equally valuable, assigning the same weight to correctly identifying someone without the disease as to correctly identifying someone with the disease, even though these two correct predictions may have vastly different consequences, different values, and different importance in the context of actual human welfare and decision-making. A system that catches no cases of disease but correctly identifies all the healthy people as healthy will score higher on a simple accuracy measure than a system that catches most cases of disease but makes some false positive mistakes along the way. Yet the first system is arguably useless for its intended purpose, while the second actually serves the genuine need it was created to address. The psychological and logical mechanism that allows this paradox to persist involves our tendency to optimize for easily quantifiable metrics rather than for the actual goals those metrics were supposed to represent, a process through which the map becomes confused with the territory, the measurement becomes confused with the thing being measured, and we end up celebrating systems that perform well on paper while failing catastrophically in practice. What makes this paradox particularly insidious is that it reveals something deeper about how we design systems and how we think about improvement and progress. Because once you understand how the accuracy paradox works, you begin to recognize that it lurks within numerous other domains and decision-making contexts where imbalanced outcomes make simple accuracy measures fundamentally misleading as guides to actual performance. This paradox persists despite having absolutely clear logical solutions, such as using precision and recall measures, confusion matrices, F1 scores, and various other metrics that are specifically designed to handle imbalanced classifications more honestly. And yet many systems continue to be built, trained, and evaluated using accuracy as a primary measure because it is the most intuitive, the easiest to understand, the most immediately appealing to people who do not think deeply about the statistical structure of their problem. We have normalized this paradox by allowing ourselves to become comfortable with the idea that a metric can be high while the system is simultaneously worthless. And we have constructed entire industries and workflows around these misleading measurements, creating a kind of institutional acceptance of a fundamental logical failure that would seem impossible to tolerate if we examined it directly rather than accepting it.